Welcome to the course on machine learning at KAUST. We will start with introduction, and in fact this will be an introductory chapter from the book Pattern Recognition and Machine Learning by Christopher Bishop. Start with defining what kind of tasks we might be dealing with when we are dealing with pattern recognition and machine learning. So imagine we have the following problem. We have some handwriting, like in the case of here, we have handwriting of some digits, and we should be able to interpret them. What is the handwriting corresponding to which digit does it correspond to? And we have a data set available, in which we have all these kind of data of some people drawing their how they write digits. We can see here one case of all the 10 digits written by one particular person, but then we can have many other examples from many other people, and all these digits are written in this kind of a little square, so that and with only one color, so that we can differentiate what is the foreground and what is the background. And the challenge here is to find a way how we can perform the assignment of these actually pixels into the correct class, which digit does it correspond to. So say that these pixels, this pattern of pixels, which are here in this one square, should be corresponding to 0 and this to 1. This could be solved, for example, by creating a specific type of rule-based system, which will try to find some patterns in the or describe patterns in this data. So let's say that maybe for describing the 0, we can try to fit some kind of a circle over various sizes, and if we are fitting a circle here over the handwritten pattern, and we perform maybe some kind of correlation or other type of expression of other type of operation between our template and the actual handwriting, we can find out how likely it is that the handwritten digit is in fact belonging to the category of 0. However, and we can do something similar for all the other digits. However, this might turn out to be relatively not very effective, because we might have a problem that, for example, number 7 might be written in some different way by others. Maybe some people write a line here, then we would need to have a rule for that as well. Some people write a different form of 4, and so on. So all this entire system would be very difficult to set up, and will be also likely prone to error. Instead, the alternative approach is, and that's the entire content of this course, is to let the machine learn from a certain training data how these representatives of these classes of digits typically look like, and learn these patterns automatically. And when a new handwritten digit comes, they will be able to classify it based on this learned form of the digit representation. So we would typically in machine learning be talking about something like an input vector x, which is in our case of these images, and an image of 784 pixels. which is 20 times 20 times image, as we have seen before, and it could be of value of floats, so 4-byte digits. Maybe it could be also a different representation, like, for example, bytes. So, and then we do not have just one image but we have n images, entire training set, as we call it. And this training set is also associated, each element within the training set is also associated with the so-called target vector T, which determines the category of the image X. And during the training or learning phase, the machine learns a certain function, which Yx, which assigns a given image into a respective category. And the output of this learned function y has the same format as the target t. So, for example, if the target t are categories of the digits, so category 0 will be for the digit 0, category 1 will be for the digit 1, and so on. So then we need to have also such categorization for this function y. Typically, we would establish kind of a tuple of this target, so it's a vector of the 10 digits, and this output y will be also a vector of 10 digits. And then for these 10 digits, but it will be represented as kind of a so in the case of the t, we can have like if we will have a coding like 1 and then followed by 9 zeros, it will be encoding 0 value. If we will have 0 and 1 and then followed by zeros, we will have 1, and so on. So in this tuple there will be only one and the rest will be zeros, and it will be defining which digit it corresponds to, whether it is the 0, 1, 2, 3, and so on. And always for which of these, where there is 1, it corresponds to that particular digit. The output of y, however, does not necessarily need to be this binary code, but it can be actually a probability distribution. So the values can vary between 0 and 1 for all the tuples, elements in this tuple, and however, their sum will need to equal to 1. So we might be a little bit uncertain whether something is 0 or 1 or 2 and so on, and this could be expressed by the values which are associated with these elements of this tuple vector describing or having the of which the y has a structure. Now, in the learning, we are not really interested in correctly determining a value of x from the training set, but in fact, we are interested in evaluating newly coming values of x, which previously our machine learning system didn't see before. And it can be then the newly learned function y of x can be applied on that new data, and it will allow us to give the classification of this newly seen digit. And this is called, this ability to being able to characterize the digits beyond the training set is called generalization. So if the system can correctly interpret the values for newly coming images which haven't been seen before, we will say that this machine learning algorithm generalizes well. If this will not be the case, then we would say that it is overfitting to the training set. And often we will be not using just a randomly represented data, but our training data will have to be somehow in a uniform format. Like, for example, we will have them in this squared representation with the same color and so on. And if it's not the case, first we will need to pre-process it into this uniform format. And also then our newly coming images in the, let's say, call them test set, will also need to be in this format before we can use the function y to determine which class they correspond to. And so far, we have been discussing within this training that we have this input vector and the target vector, and they are related in the training set. This is the example of so-called supervised learning, where we supervise the learning process by the training data associated with the corresponding target values. And once the learning process is completed, then we can use this learned representation for estimating the values of unseen data of the same type. Classification is an assignment of each input vector into a discrete category, exactly like we had in the case of categorizing these input vectors of pixels into the meaningful digits. So this is the 10 discrete categories of digits, while regression is an estimation of a continuous variable. So let's say what will be the temperature tomorrow will be an estimation of a continuous variable. So the function y will be returning not a discrete set of values, but will be returning a real value as an estimate. And then we have, in contrast to supervised learning, we have also, for example, unsupervised learning, which does not have the target values associated with the training set. And then the unsupervised learning will be able to define certain classes of similarity of the data in the training set, and they will be clustering the data into these some subclasses of this training set, and so on. They'll be able to perform some simplification of the multidimensional space of this training set into a representation in the lower dimensional spaces, so that based on the complexity of the training data, it will represent it with an appropriate representation. Like, for example, principal component analysis would be also some example of this. So it discovers distribution patterns in the data through clustering or density estimation. The last example of learning algorithms mentioned here is the so-called reinforcement learning, where we do not have really a training set in the same sense as we had in the supervised learning approach, but we have a set of sequences which eventually lead to certain reward. So imagine we are playing a chess game, and then each of these individual steps is not very clear whether it leads to winning or losing, but at the end of the game it's clear whether the game is won, lost, or the match is a draw. So and all this final outcome needs to be propagated back into the sort of some kind of into this reward. So single step is not associated with an optimal output, and we need we have this longer sequence of steps that leads to a particular outcome, measurable outcome, and then we need to assign back this outcome into credits of these individual steps. And once we, during the learning of reinforcement learning, we will have we will learn certain patterns which are beneficial in order to achieve the highest reward to win the game. and that will be called, using these patterns will be called exploitation. But during learning, one should also explore more of the patterns, and there is therefore a balance between the exploration and learning new patterns and exploitation of known good patterns. And this interplay of these two approaches will lead to a good, well trained system by means of reinforcement learning.
To explain certain concepts, let us turn to a problem of regression. In particular, we will show it on the polynomial curve fitting problem. The situation is that we have an synthetic data, which is depicted on the right-hand side, where we can see this sine curve over here, slightly offsetted from the x-axis, and then we have these blue points. These blue points represent samples of this sine curve. However, they are also perturbed by added noise. So each sample point, as you can see, they are actually sampled at kind of uniform distances from along the x dimension, and we have 10 of these samples, and from these 10 samples we want to reconstruct the curve, the green curve. We don't know the green curve, we only know the samples. That's the situation. So we have input x, which are the x coordinates, and they are associated with target t, which are the t coordinates here. And now we would like to, so we have a set of these input variables and a set of observations or targets. For using the predictions, we have decided to use a polynomial curve, where you can see here is the x powered by 0, which corresponds to 1. So this is kind of the w is kind of a biased term, and then we have which offsets actually the the um, the, the predicted model of the curve, and then we have the linear term, so x times vy, and then we have a quadratic term, x times w2, and so on, and we can define whatever curve we want to have. Do we want to have a line? Do we want to have a quadratic curve? Do we want to have a cubic curve, which tries to fit to these input sample points? So we have this sine curve, which has these perturbed values, t values, by some additive noise, and then we actually have only these samples, and our goal is to find a function which goes closely enough or exactly through these points, which we through these sample points. So how can we find this function? We have decided that our model of this function, which we will be looking for, will be actually a polynomial curve. So you can see that we have a sine function, but we want to approximate it with a polynomial. So we will never have exactly the same function in that regard. And how we do it, in principle, is that we perform just evaluation of the error given a certain function y, uh, which is this polynomial degree function, which draws us a curve between these sample points, and the target values, which are SOT, which are associated with xn, are evaluated how far away they are. So you can see it here on this picture, where we have some polynomial curve, and then we have a certain distance at a certain position xn, we measure, so we are here on the curve y, and here we measure the distance for the actual from the actual sample. And actually, this is we square this, so this is a squared error, and we sum it up for all the samples we have, for all the 10 samples. Here we have, just for convenience, a term 1/2, which we will then benefit from later. As you can see, uh, the selection of polynomial degree will affect how the curve looks like, because if we will have a line, then it will be a straight line between these points, which will somehow try to match the direction of these points. Or if it will be a quadratic curve or cubic curve, it will be a slightly curved, so that it will better approximate the shape, which is indicated by these sample points. There is also another term here, which we can see. It is called the root mean square, which is a practical term to evaluate the match of this function with respect to the sample points. And here we can see that, first of all, it is divided by the number of sample points, so it's kind of normalized, so it's independent of how many sample points we have, which is not the case of the previous error function. And then it's also a square root of it, so we actually have the same distances between our function and in our error function. Now we can see an example of this curve fitting. So first of all, if we have a zeroth order polynomial, which means just a constant function, we can still find a w term, w0 in particular, which is the offset I was mentioning, and this w term can offset our constant function so that it is somewhat closest to all the sample points, as we can see here. So this is a match if we have just our model is just a zero polynomial degree, a constant function. If you have a linear function, then the best fit of a linear function can be observed here. And we can see that this function somewhat matches the points on this sine curve, or the noise edit sine curve. If we look at the cubic curve, we can see that actually it is already matching quite well, and in fact it is even going through some of our points, and generally the match is quite good. Now, if we go for a polynomial degree of 9, we can see that this polynomial function is actually matching the sample points perfectly. It goes exactly through them. However, everywhere else it is having a very, very weird shapes, and we can see that those are extremely unlikely or far away from our original function, which is the sine function. So here we can see the effect of overfitting. We have overfitted the noised sine function. The, the function we have found is simply just perfect for the input points and its corresponding target vector, but nowhere else. And this is nicely shown in this root mean square error depicted on the right hand side. So we can see that here we have the training set, and with an increasing polynomial degree, we are somehow decreasing the root mean square error. And in fact, for the training set, we have a zero error here, so we can see that there is no error at all because we are exactly interpolating all these points. However, then we have another set, which we call test set, and this test set is a set of other points which are not depicted here. And for this test set, the function behaves or the different polynomials behave differently. So we can see that the error for our test set is slightly higher than for the training set, but it somehow with increasing polynomial degrees, it improves. And then from polynomial degree 3 to to 8, the error is roughly the same. And then for the polynomial degree 9, um, it suddenly spikes up, and we can see that this is an effect of overfitting, where the training set error it decreases and the test set error is increasing. Let's have another look at this polynomial curve fitting problem in the terms of what is happening to our ideal weights W, the W coefficients, which are associated with their x values, the input values. So if we have a just a constant function, then we can see that the non-zero is only the W0. For the linear function, there will be two non-zero W's, the W0 and W1, and so on. For it is obvious that there will be zero values for the polynomial degree 3 from the W4 there will be zeros, but for the polynomial degree 9, we will have non-zero values for all the w's. Now, this is one observation, and the other observation is that also for they are with a higher polynomial degree and with so-called higher overfitting, when the function gets more and more wild, it is associated inherently with high values of these W values. So you can see that there are very high values here, and that actually is the manifest itself through this overfitting. So the function it becomes very wild in the areas where it is not represented by these input sample values. So one idea could be because if we are talking about the polynomial degree 9, it actually also includes all the lower polynomial degrees. So it's kind of weird that if we invest the highest polynomial degree function, we are actually getting a very bad result compared to like a cubic curve. So maybe an idea could be that we can try to keep these values low, these weights, also for higher polynomial degrees, and maybe we will get a better approximation of this better regression outcome. Another strategy actually could be just even given our a large polynomial degree, so the polynomial degree of 9, but we increase the number of sample points. Instead of just 10 sample points, we will have 15, and we can see that this wild function which we observed before is actually now much well better behaving, but it's still not perfect. Now, if we increase the amount of sample points of our synthetic dataset to 100, we can see that this polynomial degree 9 is actually matching the sign function pretty well. And this means that once we um, once we have more samples, we are reducing this overfitting problem, because the polynomial degree 9 cannot interpolate through all of these 100 points, and therefore it will overall be more smooth and without these overshooting and undershooting effects. But it's kind of weird that we are somehow conditioning our model to be good or bad just by the number of samples, that it is dependent on the number of samples. Maybe we can find a better way to um, to control um, this determination of the y function with the high polynomial degree, and that is by trying to get the weights of the W of lower values and not in millions and hundred thousands as we have observed on the previous table. One solution to this problem is the so-called regularization. So regularization is a that we is a way that we are changing our error function. We are slightly modifying it to take into consideration certain constraints. And one of our constraints here now is, as we said, is that we want that our W values will be relatively small. So here we have to our already known error function, which we have been using before, we are adding a term which is having the W values, and we want to overall minimize this. So also this term should be minimized. And this term contributes to the overall error function by a certain amount lambda. So this is this lambda term is defining how much the regularizer will have effect on this on the overall function. So the higher the lambda value, the smaller this weight W will be at the end. If the lambda value is 0, it will turn into our previous value where we had these very high values associated with W's for the polynomial degree 9. So, and this is called a shrinkage method or a ridge regression or a weight decay where the strategy is to simply lower these values W or associated with these values W. You can see here what this term actually means. So this is a vector notation, and it basically means a dot product with itself. And we want to minimize this sum along with the overall edge of the function. And here we can see the result. So we observe that for a certain lambda, here we have the lambda which is somewhere between 0 and 1 and rather close to 0. We have here, so it's not very high a lambda value, maybe 0.2 or something like that. We can see that the match for the polynomial degree 9 is actually very good. Now, what happens if we increase the lambda? So the lambda here is equal to, what is it equal to? If ln lambda is 0, then lambda is 1. And for lambda 1, it means that lambda half was the weight term for contribution of the W's. So we have the 1/2 of the overall weights is somehow part of this error function. The regularization term is very strong, and we see that the weights are then really very strongly pushed towards 0, and we almost get the constant function. Here is the outcome of this different lambda. So lambda ln lambda equals minus infinity. Well, that is basically when lambda is 0, and we see the original terms which are very high. We can see it here also on the right hand side on this graph, where we have the training set error is 0, and here we have the, the, the test set error is very high on this root mean square error metric. Now we are increasing the lambda from 0 to 1 towards 1, but not quite 1, really between 0 and maybe 0.3 or something like that. And then we can see that the error is kept is massively decreasing for the test set, and it's somewhat constant in this region between ln lambda minus 35 to minus 25. and then the error starts to be increasing because we are over regularizing this error term. And we can see for the ln lambda is equals to 0, we have very, very small values, also somehow depicting that we are dealing with the constant function. This is a kind of a W is kind of a special case because we should not really regularize the W0 because we do not want to keep it close to 0. If we have a certain offset of the function, this offset should be maintained even during this regularization. Although you can see that admittedly here this W0 term is smaller than in the other cases.
On the previous lecture, we have introduced the typical problem of machine learning where we are searching for an estimate of a continuous variable, and which is called regression. And we have been talking about the aspects which are related to it, which means, for example, what will be our function, which we are wanting to estimate the new values with. How does the model of our machine learning model should look like? And we have been talking about data sizes, we have been talking about regularization, and we also we've been mentioning like some optimal weights W given a certain model. Like for example, for a constant model, we said there is a certain weight V0, W0, sorry, which for which this model will be the optimal, so will give the best estimates of newly predicted values T. However, we didn't really talk about how do we perform this estimation. And the nice thing on the linear regression or for regression using linear models in general is that they do have a closed form solution, meaning that we do not need to perform finding those values W, these weights, through an iterative process of optimization, but we can actually calculate them based on a closed form formula. So how do we get to that? We will be using a technique called maximal likelihood estimation, and it is clarified on this slide with the first example. So imagine that we want to perform linear regression search for the best values W. For that, we take already the error function we have been talking about on the last lecture, where we have the difference between the function we are looking for, the value, the function y, and the actual values we know for certain points xn. So we know the pairs x1, t1, x2, t2, and so on. And we are looking for an difference which will be the smallest given some optimal values of w. Now, and this is then summed up into and forming the error. Observe that there is the 2 here for this error, but I took the 1/2 which was previously here to the left side. Now, this equation, if we calculate out the square, will be equal to the term on next to it, because first of all, we have changed our function y, which is a function of x and or x and w, into its linear regression form, where we have the value weight w0 and the weight w1, where the weight w1 is associated with the x powered by 1. So that's our y, really. Now, so that is one form which we can work with, because now we have in this equation values w0 and w1 which we want to calculate. Now, a key insight is that this function has based on the w, the error function will be maybe big or small, and it will be it's a function. And we know that from even middle school or high school math, that that if we want to study a function, we can look at its derivatives and see where it has a maxima, minima, or maybe some inflection points, stationary points. So that's what we are going to do now, in fact. So we take this equation, this form, and we calculate a derivative of it. And we calculate the derivative first of with respect to the partial derivative with respect to the value w0. Now, here is the calculation of the derivative, where you can see here is now 2 because we had a squared, so the square so this term with respect to w0 is this term because it's this formula without the square here, but with 2 here, and times, and derivative of w0 is 1, so this is the formula. Now, we put it equal to 0, which means that we want to find the extremal values or the stationary values. And from that, we calculate the values, what needs to be now the w0. So we put the w0 on one hand side and the other values, the w1 and xn and tn, on the other side of the equation. Now, w0 is in the sum term constant, so we can take it out of this sum, and w0 simply will be just n times w0 from this sum, obviously, because we are separating this sum into several sum terms. So here first we have on the left hand side, we got rid of the 2 first of all in the beginning, and then we see that nw0 is equal to, and then we have this term, sum of Tn, which is positive. On the left-hand side, it was negative. The right-hand side is positive, minus, and now again, for this term, we can take out the W1 minus W1 times sum of Xn. And now, if we observe these two terms, so this term is actually like a sum of all the n's we have, and if we would divide it by the n, then it will be an average of the tn's which we have. And the same holds here. If we would divide the xn by this sum by n, then we will have the average. In fact, we have the n associated here with this with our w0. So what we do is we just put the n on the right hand side, and we end up with a formula for w0, which is w0 is equal to average of t's minus v1 average of x. So that is the closed form solution for w0. Now we will use this term for in the next slide for calculating the w1, because as we can see here, the w0 is dependent on the value w1, and we don't know the w1 yet. So let's calculate the value w1, which is associated and determining as the slope of this linear regression function. We use the same strategy for calculating the W1. So we have a look at our error function again, and we are now, instead of putting the term, we also perform the derivative with respect to the W1 of our error function, and we also, so this is this result, and then we also put, instead of the W0, we put the values which we already have calculated. W0 must be equal to, so which is the average t minus W1 times average x. And that we now reformulate into sum of several sums. Observe that as compared to the previous partial derivative, here we have the term xn, because deriving this term, w1 times xn, will result into xn. So we multiply by this. This causes that for this function, and we have the term 2 times w0, and then we have the xn term, which is in the sum, so sum of xn. And then we have the second term, 2 times w1, and here we have xn squared. Why is it xn squared? Because we have here xn, here we have xn, this is xn squared, and then we have minus 2 times Tn times xn. I think this is pretty obvious. From this, we can again isolate the w1 and put everything on else, all the other variables, on the right-hand side. That will be the strategy. So let's have a look. So here we have one term which contains the w1, and this is another term which contains the w1. So we are putting these two together, where we have the xn squared minus average x and sum of xn, which corresponds to these first two terms. And then we are left out with x and tn, that's this term, and then minus average t xn. This is this term multiplied with this. So, and observe that we have also got rid of the 2 because this equation is equal to 0, as we want to minimize it by finding the minimal value of w. So actually the value of w or w's for which the error function is minimal. Okay, so now we have this expression, and we can also see that this sum here now for the next step is sum of xn. So that's like n times average x, because this sum divided by n would be an average x. So if it's not divided by n, it's like n times average x. We can see it here. The same holds for this term, where we have n times average x average t. Okay, and then this is equal to, so this term here is equal to this term. And why is it equal to this term? So we can have a look here. So we can see that term again, once again here. When we multiply it out, we end up with these terms in the sum, overall sum. And then, so we can separate it into these individual sums. Here we see that already 1 times is n times n xx, but here we also have x time, and this is also an average x, and this one is also n times average x. So this is minus, is plus. We can see the more clearer here, minus, plus. So this is equal to x squared minus n average x. And that's why we came to this term from this term, because we just shown that they are equal to each other. And this could be also then seen on the right-hand side, where we have not twice the same term, but we have term xn minus average x and tn minus average t, because we have this term here, and analogously we could have this term calculated out, and we will end up in the same reformulation. Now we have everything ready to express the w1 by just dividing by this term from the left-hand side, and you can see that we have only the xn's and average x and tn's and average t to express as the w1 value. From this w1 value, we will be then calculating the w0 value based on the equation from the last slide. So with this, we have found a closed form solution which gives us the a function of a line which will be in the sum of squares of errors, giving us the minimal error if given the W0 and W1. It doesn't mean that that's actually the function. That's just the model gives us this, this function with minimal value of our weights W. Let's have a look at the same thing once again, but this time in a vector or a matrix formulation. So our function y is equal to this time a matrix X times a vector W. This is generally for linear models, and for our linear regression problem, the W vector will consist of two elements, W0 and W1, and so it will be having some vector of RD, where the D will be 2, and the X is the matrix where we have it's called the design matrix or data matrix, which we will be talking about in detail later. And this matrix will contain the X powered by 0 in one column and X powered by 1 in the other column, where each row will determine one data point. And so we will have, in fact, a matrix X, which will be having n rows, and it will have B columns, which means 2 columns, where one column will constitute only ones, and the second column will have the values x1 to xn. So now we again turn this vector form to our error term, which we have here, which is now the symbol for sum is out because we are in the vector formulation, and we see that this is equal to the minimal, or actually it's like a dot product of this vector. And we replace the y with xw, and xw minus t will be now for best w's, it will be giving us the smallest error, which is, you can see that this turns into a vector, and this is a vector already, and vector transpose with itself will form a dot product. So we will have a scalar value coming out of this at the end. But instead, let's calculate out this term, which is equal to like xw transpose xw. So we have this xw transpose xw. Then we have minus 2 t transpose xw. So that's coming from these two terms and these two terms. And then we have plus t transpose t, which is the multiplication of these two vectors and the scalar product of it. Now, if we change this formulation into this formulation, which is one of the matrix operations of transpose, then we observe that we have one form of our vectors and matrices, which we will then be able to perform derivative of, because we again want to make a derivative and make it equal to 0. The second term, this term, we slightly reformulate, where we put together the x and t as a transpose with w, so that we can easier perform the derivative. And now let's perform the derivative of this function, and we see that the first term is now 2x transpose xw. And how did we come to this? So this is a known result from matrix calculus, where we have this type of formulation, and we are having the derivative with respect to the vector W is equal to A plus A transpose W. And for symmetric matrices, this will be 2AW. And we have this is a matrix, and we know that this kind of matrix, or better to say, this kind of matrix is a symmetric one. So therefore, W transpose symmetric matrix W is equal to 2 times the symmetric matrix W as a derivative. For the second term, we already, this is another result of matrix calculus, that this term transpose W derived will be this term inside the brackets. So we have it here, and of course the 2. So this is the derivative of our error term. And if it's equal to 0, then we can formulate what will be. We put again the W on the left-hand side with its associated terms, and the other term, this one, on the right-hand side, which we did here. Obviously, this term under the derivative disappears because it doesn't have any association with W. Now we just take this term and put it to the right-hand side to isolate the W, and here we have the vector form of the closed form calculation of the W's, for which the linear regression, or in general a linear model, will have the smallest sum of squared errors. Next example, let's have a look at again the same thing, namely the vector formulation of this error term, but this time we will add the regularization term to it. So you remember from the last class, in order to have as small w's as possible, we have here this regularization with the term lambda. And now we are again calculating reformulating this slightly. So we are putting here the xw as we did before, and then this term we reformulate into this form of the vector dot product, and we end up in already the expected terms, this one and this one and this one, as we had before, exactly before, plus the term associated with lambda, the regularization term. Now, what we do next, again, we try to find the minimum, and to find the minimum of this function, we are performing the derivative with respect to the W, and then, but this time also including the regularization term, which ends up in this formula. So we know already the first two terms. The third term is not associated with any W here, so that disappears. And the term for the lambda is then just 2 lambda W. And so we have here the W, and we have on this term the W, so we keep that on the left-hand side. And here we are just getting rid of the 2, value 2, and we are having this term from the previous equation, and then instead of just lambda, we have, because this is a sum of two matrices, we associate the lambda with an identity matrix, create basically a diagonal matrix, which will be then summed up with this symmetric matrix. And then on the right-hand side, we will have the term as before, the x transpose t. And now we put the term from the left-hand side, the W was multiplied with, to the left-hand side by inverse from the inverse, putting the inverse from the left, and we have the final term for our linear regression with also including regularization. In this introductory part, we will now have a look at the probability theory basics so that we can use this knowledge for later understanding various complex machine learning models. So let's start with reviewing some concepts. Imagine we have two random variables x, y. Now let's have a look at an illustrative example. We have two random variables here. One random variable is the random variable which takes two values, and the two values will be which box is which. So let's say the random variable x gets the value either red or blue, and we can pick the one box or the other with a certain probability. Then the second random variable will be the random variable y, which will be fruits. Like, for example, here we have oranges, and here we have apples, and we can pick one or the other, and so we will get either O for orange or A as apple for the random variable y. Now, these two are obviously in some relation with each other because we will be picking fruits from certain boxes, and this box, so the boxes are associated with the random variable x, and the fruits are associated with the random variable y. Then, so we can see here that we have some values. So in this case, the xi will be the R or B for red and blue, and the yj's will be either O or A. And then we can perform this operation of picking fruits multiple times. So we are talking about n trials. And n1j is a number of trials which result into x equals xi and y equals yj. That means here on this illustrative example that, let's say, nij for will be, let's say, n x1 will be red and y1 will be orange, let's say, then ny1j and 1, will be a situation where we put the hand into the red box and took out an orange. And if this event, we repeat these trials many times, and we sum up the amount of trials where this event happened into the value n11. Now let's have a look at this representation here, which shows us these two variables. These are now no longer the apples and oranges and the boxes. It's more general, where we have a value xi, which can take up 1, 2, 3, 4, 5 different values, and the random variable y can take up 3 different values. And we can see here that if xi and yi happens, then the nij is the sum of the events where x was equal to xi and y was equal to yj. Also, we can see certain rows. So this row is full of these events, of these so-called joint events. But if we just sum up this row, we will sum up how many events have happened where there was an xj, y was equal to yj, irrespective of the x. And so that is the overall sum of events when y was equal to yj from overall n trials. And that is equal to the value Rj. So R stands here for row. And analogously, we can also sum up the values in the column, and we will come up with values which are, or value for which the x equals to xi, no matter what the y value was. Okay. Is characterizing the various trials, and each element in this grid will then be one trial which belongs to one category for one particular value of a random variable. And we can see that we are establishing here something which we call as a joint probability, which is, for example, in one cell we have number of particular trials where x has the value xi and y has the value of yj. And this number of trials, if we divide it by the total number of trials, then we have a value between 0 and 1 which characterizes the joint probability. And such a joint probability we can calculate for each of these cells, and that joint probability will characterize the kind of a histogram or occurrence. How probable is that the two variables will be in some constellation where one will be having one value and at the same time the other one will have another value. So that's the joint probability. Out of this joint probability, Nij divided by n, we can calculate also something which is called the marginal probability. And this marginal probability is essentially calculating for each column, for the x or for each row for y, what is the total probability of x or y having a certain value. So for example, here we can see that the marginal probability will be summing up the number of occurrences of Nij and Nij plus 1 and Nij minus 1, you could say, where and this whole divided then by the number of all trials. So this Ci is the sum of all events which are in this column divided by the number of trials overall. And that is using the so-called sum rule in probability, where we are summing up all the joint probabilities for along the other variable. So here we see that j is equal to 1 to L, and we go over all y's, while the x is kept constant, x equals xi. And then out of that we will obtain the marginal probability of p equals xi. Now the other principle in probability theory is the so-called product rule. Let's introduce now another concept which is called the so-called conditional probability. So we have so far had the joint probability, which was about the probability of the two random variables having some specific combination of values. And then we have the marginal probability, where we are concerned just with one random variable and probability of obtaining specific values of that one. And the conditional probability is we can see here, for example, here is the joint probability of Ni, or here is the Nij, the number of trials for one particular cell, and for joint probability, we will divide it by the all trials and in the whole space. While for the conditional probability, we are dividing it by the amount of trials in this column. And it means the probability of y having specific value after we observed for x some particular value xi. So that's a condition. Given that we have observed x equals xi, what is the probability of y having the value of yj, and it can be calculated by the fraction of number of trials in one cell divided the number of trials in one column for obtaining the conditional probability for y. Obviously, or analogously, we can calculate conditional probability also by fixing y to specific value, and the x will be we will obtain the value of x given a certain y value. And then we will be dividing the cell on amount of events divided by the events which are in the same row in this conceptual space. And for the product rule, we can see that we have the joint probability, which is equal, we already know now, nij divided by n, the total number of trials, is also equal to, imagine that we multiply it by 1, and 1 will be like fraction of ci divided by ci. So that is 1. So we are now kind of infiltrating here the fraction ci divided by ci, and we multiply it with it, but it actually gets a new meaning, because we can see here that the joint probability is in fact equal to, what is this? This is in fact the marginal probability, and in column that's of x, and here in this part is the conditional probability, which is the nij divided by all the events happening in the column ci. So we can see that the joint probability is a product of the conditional probability given x having the value xi, what is the probability of y having the value yj, multiplied by the probability of x. We can all see now in this example, which is explaining the so-called bias theorem. We have again here some amount of trials depicted by these blue dots, and our two variables, x and y, are obtaining some two values, y equals 1 and y equals 2. And then, so it's just two different values for the random variable y, and for x is 1, 2, 3, 4, 5, 6, 7, 8, 9, if I counted well, of different discrete values which the variable x can have. And this number of events which are happening here are encoding as the overall probability. So the probability of x having a certain value, for example, will be number of these trials divided by the total amount of values, and we can see the result here. So this will be the marginal probability for this particular value of x. And we can see here that it is relatively kind of distributed along this kind of a Gaussian type of lobe here, while if we look at the distribution for the y, we see that this distribution, the y equals 2, is slightly less probable than the distribution of y equals 1. Now this drawing is also showing us the conditional probability, and here is how we can interpret it. So there is the probability distribution given that y is equal to 1. So now we are only concentrating on this lower part, and we are seeing how is the overall distribution of the events. We can observe that for the most tried cells, there is almost no in fact, events occurring in the bottom part, and therefore the probability is equal to 0 there. So this probability of the conditional probability is kind of skewed towards the left. As we can see, there are much more events happening in the left on this bottom than or rather on the right side. Now let's have a look at this fundamental theorem called bias theorem. It says that you can actually imagine that as if this px would be on the left hand side. So the px times py given certain x would mean actually the joint probability of pxy. So that will characterize the joint probability distribution of these two random variables. And analogously, also, if we just flip these two probabilities, so the conditional probability of x given a certain y multiplied by py is also the joint probability. So if this px would be here, they both are equal to the same joint probability pxy. Now we take the px to one side, and then we can calculate the conditional probability from another conditional probability and other marginal probabilities. And this is what the Bayes theorem is telling us. We will see it soon on an example. So the example is already here. We have seen before this example of red and blue box and the fruits which are in this red and blue box, the orange one, the oranges, and the green one, which are depicting the apples. So we have two random variables, the b, which obtains the discrete values of r or b, and then as box, the capital B, and then fruits for f, and it has obtains the discrete values of either a or o. For some reason, the selection of the box is biased, and it is a little bit less likely that the red box is being picked, and a little bit more likely that the blue box is being picked. Observe that this 0.4 probability and 0.6 probability together in sum equal 1, because there is no other choice than these two boxes. One of them will be picked in an event, in a trial. And part of this trial is also that a fruit is being picked from one of these boxes. So, and now we can see the conditional probability that a apple is being picked from a red box is 1/4 here, which means also actually 2/8. We can see that there are 2 apples and overall 8 fruits. So that's why it's 1/4. The conditional probability of picking orange from the red box is 3/4, so 0.5, and so 0.75, which also we can see directly from here. So there is 6 divided by 8, which equals 3/4. And the same exercise once again for the blue box. We can see that the probability of apples is higher here, conditional probability, and it's 3/4, and the conditional probability for picking orange is just 1/4. And observe that these conditional probabilities, the 1/4 plus 3/4 is equal to 1, and as well this 3/4 plus 1/4 is also equal to 1. Now, let's try to solve another problem. First, what is the probability of picking an apple overall? So not from a specific box, not a conditional probability, but in fact a marginal probability. And the probability of picking an apple is the joint probability where we have and for 2 different boxes. So here we have in the box red box is the probability of picking the red box times the conditional probability that if we take the red box, what is the probability of an apple? So this product is one part of the probability of picking an apple, and then the other part is if we would be picking the blue box. So the blue box is the probability here, and given that we pick the blue box, then the probability of picking an apple is this conditional probability. We sum these two up, and we end up in the overall probability of 11/20 to be the probability of picking an apple. As we can only pick one of the two fruits, and in sum the probability is 1 of picking a fruit, then the probability of picking an orange is 1 minus probability of picking an apple, and this is equal to 9/20. Then An interesting question is, given that we have picked an orange, what is the probability that the box was red? So we are now turning this conditional probability where the fixed random variable is the fruit, and the probability we are observing is with respect to the boxes. Now we can see that here we can apply the Bayes theorem, because we already know the probability of an orange if we pick the red box, and probability of picking the red box overall, and we divide it by the probability of picking an orange, which is the 9/20th, which we just calculated, and then we obtain the conditional probability of picking the red box in case that we have picked an orange. And indeed, if you observe this, the chance that we have picked an orange, that it was in the red box, seems to be more likely. So we have here two cases. Before we knew which fruit was being picked, we would say the probability of the picking the something from the red box would be 0.4. And then after this event happened, its probability has changed into this conditional probability, which is 2/3, so which is higher in fact. We have increased the chance that actually the fruit was picked from the red box after observing the event of picking a fruit being an orange. Now, we can interpret this as observations before event happens and after event happens. So we can talk about so-called prior probability before the event happened, and the prior probability would be actually the marginal probability of the event, and then we have the so-called posterior probability, which will be corresponding to the conditional probability that an event happened and that determine the value of y, and then we see that a change in the probability with respect to x is happening. And in case we have a joint probability, but these two events are not having such a relationship as boxes in, and apples and fruits in these boxes, but we have like totally unrelated events, like for example picking a box, which color of the box, and whether it will be raining or not on that day. These are seemingly unrelated events, and therefore they are in this, we call that these two probability distributions are independent from each other. So even if we observe that x has changed, let's say it was we picked the red box, it still doesn't mean that there is a higher likelihood that it will be sunny or a rainy day. So the probability of y didn't change with respect to that. So we can say that in that case of independent distributions, the prior and the posterior probability are the same. And in such a case, the joint probability is a product of these two marginal probabilities, or the prior probabilities of px and py. Let's have a look at the case of continuous random variables. So far, we have been dealing with discrete random variables, which are obtaining certain discrete values, like boxes having certain colors, or fruits being of certain type. But now let's have a look at continuous random variable, where we have a so-called probability density function, px, which is a function which is a non-negative function, and its integral in the sum is equal to 1 over its entire range. And the probability is defined on a certain interval of x. So if x is having some specific value, that only some specific value, the probability is 0. But if you are saying that the probability is between x having value let's say 0.3 and 0.35, there is a certain probability that the x will have such certain value, and it is calculated by integrating this probability density function. And if we integrate the probability density function from its, let's say, beginning, or from minus infinity up to a certain real value z, then we have the so-called cumulative distribution function, capital PZ. And we can see that plotted here, which is an increasing function, which is could be also monotonically increasing, but it's generally an increasing function, and its value is equal to the integral. At the end, you could say its value is equal to the integral from minus infinity to plus infinity bx dx, which is 1. Now, if we want to find out what is the marginal probability in this for this continuous random variable, then we see that we can kind of integrate out from the joint probability one of the variables. So we have here a joint probability pxy in the integral dy, and that will this integral will give us the marginal probability of x. Also, in this case, the joint probability can be calculated as a product of the conditional probability and the marginal probability. So, for example, the px times the p of y given x. Now, one interesting property of this continuous random variable occurs in the change of variables situation. So imagine we have p of x probability density function, or px of x probability density function here, and this random variable x can be obtained also by having a random variable y and as an argument of a function g. So we can see here that we are changing the variable x with the variable y. And that will actually change also the probability distribution. And how? It will be basically governed by the structure of this function g of y. So we can see that x is equal to gy here. Therefore, if we perform the derivative, then the dx is equal to g prime y dy. And now this is a key equation here, which is telling us that probability on some infinitely small interval of pi of y dy is equal to the same product of the probability of x dx. So the same probability of a certain interval, we can see that the kind of the area of one of these blue elements must be the same as the area of some corresponding blue element. And here you can see that this distribution is kind of dense in this area, and this function, this nonlinear function, is making it differently shaped or distributed along the y-axis. And as this is the case, then we can see that some of these kind of these rectangles representing these very small areas, rectangular areas, are actually a little bit less densely spaced along the y, and that is governed by the g, in fact. So what has to be preserved is that the probability is somehow given the function stretching or putting densifying the the other probability, the overall probability has to remain the same for that particular area. So the probability of y dy times dy has to be equal to the px of x dx. Now, if we have the probability y or py of y dy, then, and we now we change the variable of x with gy, and then we change also the dx with g prime dy. So this is the result. We can see that the change of variable has brought us this term, which is causing this kind of scaling of this scaling factor. Now we can also interpret it as the ratio of dx and dy, and it's in absolute values here, and also it is in absolute values in this case here, because it doesn't matter whether the function is going up or going down, but it's more whether it is dilating or making it densifying the distribution by the change of variable. And we can also talk about a Jacobian, which this term is characterizing. So the change of variable is also governed by this function, which is utilized in this change of variable. And that has one important consequence, and that means that, for example, the maximal value of a certain probability is could be changed by, so let's say the mode, the highest, where the highest value is, can be changed by the change of variable. And the function, which is in this case a nonlinear function, can change the probability distribution shape accordingly. Now, one interesting characteristic of a function f of x, which is a random variable, either continuous or discrete one, is expectation. Expectation of function fx is an average value of f under some probability distribution px. So the x variable has a certain probability distribution. So it's more probable that some values of x will be occurring than some other ones. And once we have a certain value, obtaining a certain value x, that is an argument of this function f. So this will result of an expected value of this function, meaning, like, if we have this function, what would be the most likely outcome of that function, given a certain probability distribution of the random variable, which is its argument. So here we can see the formula for that, which is simply the product of the probability of x times the function of x for all the random variable values which it can have in the discrete case. So with this, we will have kind of a weighted function. And if we have a uniform distribution, then this px will be 1 divided by total number of the states or the values which this random variable can have. For the continuous case, this sum is replaced by an integral where we have the px is multiplied, the probability density function, by the fx dx. Now, the expectation of a certain function, if we have a certain samples and we do not know the underlying probability distribution, we can say that an expectation of this function could be equal to the sum of all the sampled values, and as an argument, a function of a value of that, divided by the total number of trials. And of course, if our total number of trials so far is just 1, then we will be maybe a little bit far away from the expectation, real true expectation of that function with respect to the unknown probability distribution. But with an increasing n, if we have the n equals 1,000, million, or billion, we will increasingly, this sum normalized will be increasingly closer and closer to the true expectation of f. We have also the concept of a conditional expectation, which is an expectation with a certain with respect to certain conditional distribution. So px given y. And so nothing is changing, only that here we have a conditional probability instead of the marginal conditional probability instead of the marginal probability or the probability of the single variable. And you can interpret it in in the following way. Imagine that you are having a probability distribution of x, which is giving you a certain probability of the number of, let's say, jelly beans in a bag of sweets. Now, this number of jelly beans can be varying. Maybe it's 30, sometimes it's 31, 32, maybe even 25. So there is a certain probability distribution associated with that number. And then, so that would be of all these bags which are containing the jelly beans, there will be some probability distribution. And if you want to take some conditional distribution, you can say a probability of the number of jelly beans in a bag from a certain brand of sweets. And that is that we are fixing the y variable, which would correspond to the brand choice, to a particular brand. And that will cause us this conditional distribution and then the conditional expectation. So we condition this expectation with some other random variable. It is also interesting to observe a different property of a random distribution, which is called the variance. Variance of a function is a measure how much variability is there of fx around the expected value of fx. So also, as the fx is linked with the probability distribution of the random variable x, how much is this probability distribution spread around or concentrated around the most likely choice of x. And we can see it here. What is the variance of a function equal to? It is an expectation, average of the distance, you could say, of a function value from the expected function value squared. So this is the property, this is the definition of the variance. Now, so we have a certain function, we have a certain expectation of that function, and then we have an expectation of this. So we can apply these rules for calculating these expectations with these sums and product with the probability to obtain these corresponding values. Now, we can also slightly reformulate that. For example, that we multiply out this square formulation here, and we will have fx squared minus 2fx efx plus 2fx squared. And we can then separate this into several expectations. One expectation with respect to fx squared, then minus expectation of fx 2fx squared. Where does this come from? This comes from, this is the product of expectation of fx, and then, but expectation also of this fx, so these two are then fx squared, in fact, as we can see here, and it's 2 because of the 2 over here. and then plus, and then the last term is this plus expectation of fx squared, which leaves us with expectation of argument fx squared minus expectations of fx and the whole thing squared. So that is also another formula of variance which we can use. Variance as such we measure with respect to the random variable or function itself of this random variable. We have another quantity which is called the covariance, which describes us how the y and x, two different random variables, are somehow correlated. How much do they vary together? And if they are correlated, where the x is, let's say, changing a lot, and at the same time y is changing a lot, then we have a positive covariance. And if we have it's positively changing, and if we have a positive change in x but a negative change in y, then we have a negative covariance. We can see the covariance definition here. So that would be an expectation of similar to the variance, but here now instead of having this squared term, we have one term with respect to the random variable x and product with another term which measures somehow the distance of y from this expectation of y. So here we can see that we multiply this product and then we actually perform this for all the combinations of x and y. So this would be, let's say, for a discrete variable, the covariance will be, we will take all the combinations of x and y, and we will before that calculate an expectation for the random variable x separately, an expectation of the random variable y separately, so that we have these, and then we will then calculate this sum or the subtraction for each separately, and then we will multiply that, and then we will sum it up and average it together by some normalization of occurrences of the all trials. Now, for the multivariate case, we have something called the covariance matrix. For multivariate case, by that we mean that the random variable x is no longer a scalar in the sense that it's one random variable which can have, let's say, 5 different values. But in fact, it's a vector of random variables. So it has this vector has in itself a random variable of its element x1, x2, x3, x4, say 2xn, and the same for this vector y. And if we have these two vectors of random variables, we also want to understand the covariance. But the covariance is no longer a scalar value, as it was the case for the single variate case of x and y, but it is actually a covariance matrix where we are observing the covariance for each of the elements of these vectors. So here, in this case, we therefore calculate for the expectation value for each element in x, for each coordinate or element within this vector of x, and then we are calculating the distance to this expectation value. And we perform the same thing for y and calculate here the product. In fact, this will then be a dot product, which will then be calculating, actually it will be an outer product, and it will be calculating in the way as it is similarly as it is depicted here. So in this case we have here x1, x2, x3 and y1, y2, y3, and this outer product is calculated in a way where we have basically all the combinations of these multiplications, and obviously this matrix will therefore be a symmetric matrix because the multiplication is an commutative it's a commutative operation. Now, this is not the covariance matrix we will be calculating right away like this, because we have also here this subtraction term from the expectation value. So here actually there should be always minus expectation of x1 minus expectation of x2 minus expectation of x3, and analogously here also for the y's. But here this is how we calculate the outer product, which is forming this covariance matrix. And this covariance matrix can also be calculated from the same multivariate distribution. So covariance matrix within which studies how the different elements of a certain vector are co-varying together. So it does not necessarily need to be two different vectors of random variables. It could be the same ones, as it is the case here, where we have this capital sigma as a symbol for that. Related to the previous slide, I also wanted to mention what this covariance matrix might mean. Imagine a student case. Like in your case, you will also have an exam of 40 scores at the end of the semester, and each exam will be graded by a certain score. And let's say that's one random variable, and each trial of this random variable corresponds to one student. And then we have also, for the same student, we have another random variable, the probability distribution, which characterizes the duration of the preparation on the exam. So some students have been preparing for the exam 1 day, another student has been preparing 3 days, and overall we have a certain probability distribution of the how long did the students have been preparing for the exam, and another random variable, what was the grade. And now we want to study how do they correlate. So first we will calculate for these two let's say elements of a vector, either it could be, or different let's say elements of a vector of these students. We will calculate the average time which was spent on preparing for an exam and an average grade. And then this we will subtract from each student's duration for preparation and from each student's the grade. And then we will then perform this outer product of these values, and we will see on the matrix how does the preparation of the for the exam correlate in case of these students with the final grade. Now let's turn the page and let's talk about the different interpretation of probability theory. So one view which is used in probability theory is the so-called frequentist view, and we have already seen it on the case of calculating, let's say, the linear regression, or of the case of general linear models for regression. We were trying to find the weights, the parameters, let's say, of a curve, which would fit our sample data the best. And those corresponding parameters were then picked to characterize our probability distribution. That's one way of dealing with the probabilities. Another way says that while you have certain trials which you have performed, you might also have some prior information about the distribution. So for example, imagine the situation that we are throwing a coin, and for some reason this coin, we have three events, and each time it will be the head which will show up. In case of this frequentist view, we will say that the probability that the head is coming is 1, and the probability that the tail is will be shown is 0, which for a fair coin will definitely not be the case. So it would be better to introduce some prior, which also sets, for example, that the fair dice have a 50% chance of each of these having each of these two values, which can then characterize the probability distribution better, especially in the case of only few trials. So it kind of compensates maybe for a lack of observed data. And that we can see in the case of the so-called Bayesian view, that we have not only the data from the frequentist view, like and the probabilities associated from these experiments, but we have also the prior view on and probabilities associated with that type of events. So we see that a certain, because this is the Bayes theorem as we can recognize it, we can see that the probability, marginal probability of the weights W is multiplied with the marginal probability, the conditional probability of data given these weights, is actually proportional to the so-called posterior distribution, and this probability of the data, in this case data term, is the normalizing factor. So, but overall, we can see that even if we do not perform this normalization, that the posterior probability is proportional to the product of the prior probability and the likelihood. So in the case of the fair coin, even if we have 3 times the outcome is the head, the prior will say that the probability is only 50% for the head, and will compensate for this chance which occurred, for this unlikely chance of occurrence 3 consecutive heads. And this posterior probability distribution expresses the uncertainty in W after observing the D. So before observing the data, we have our prior, and after observing this data, we have this posterior probability distribution. So it is characterized by this prior and this so-called likelihood function, which is this part which we have, for example, calculated in this case of linear regression according to this closed form example before. Now, before we turn this into practice, let's have a look at the Gaussian distribution as one of the fundamental distributions in probability theory. The Gaussian distribution is a so-called unimodal distribution. It has one peak, and it is having, in fact, an infinite extent, so it doesn't have 0 probability anywhere, it is characterized by this exponential formula, where we have e powered by x minus mu squared divided by 2 sigma squared. And then we have this normalization term, 1 divided by square root 2 pi sigma squared, which just ensures that this so-called normal distribution is normalized, so the overall integral from minus infinity to infinity of this function will be equal to 1. So, and there are various properties of these values here. So we have our random variable x here of this continuous, which is a continuous random variable, and it has an associated probability from this normal distribution. And this normal distribution has two parameters. One is mu and one is sigma squared. The mu is the mean of this probability distribution, and it's also the expectation of this probability distribution. And then we have the sigma squared, which is in fact the variance of this distribution, and this parameter, making it bigger, will make the Gaussian load to be more spread, and making it smaller will make the Gaussian load to be more centered around the mean. And then we have some other replacement kind of characteristics. For example, the reciprocal of the variance is the precision, beta. And also the square root of the variance, the sigma itself, is called the standard deviation. Now we can see here that the expectation of the Gaussian probability distribution is mu, and that the variance, we will see that it is equal to the sigma squared. But let's have a look at it. Why is that the case? So please notice that the expectation of a continuous random variable is calculated from its probability distribution and then the function. And the function is now the value x itself. So it's like fx equals x. So this is now the product of the x times px, which happens to be this exponential function normalized. Now, in order to calculate this integral, let's make a change of variable, and here we will replace the x minus mu divided by sigma with a certain variable z. So now, if z is this fraction, then x is equal to mu plus sigma z, obviously, because we put the sigma on the left-hand side, and plus mu, and then we have the value for the x, and then what is the value for dx? So if we derive this formula, the dx will be sigma dz. So now we can put this and replace it. So now instead of x, we put here mu plus sigma z, and then this formula where we, instead of x, put here this function of z, mu plus sigma z minus mu squared. So we still recognize this exponential term, and then instead of dx, we put here sigma dz. Now, what is this equal to? So if we can see that this part turns out to be the z squared divided by 2, because the z was equal to x minus mu divided by sigma. So, and that was squared there before, so it corresponds to z squared. And the rest is remains the same. And furthermore, we can then multiply this term out. So mu is not changing because it's not associated with z. So we have mu here in front of the integral, and then we have this e powered by minus z squared divided by 2 plus sigma z times e powered by minus z squared divided by 2. Now, without really knowing the value of this integral, or value of this integral, we know that this function is in fact a even one. So in this case, if this is and this function, it is known result from calculus, is actually equal to the value square root of 2 pi. Okay. However, this function, if this is an even function, this function must be times with the product with z must be an odd function, and an integral of an odd function is 0. So this term vanishes, and this term is mu times square root of 2 pi. But we already have a 2 pi here from before, as you notice, and therefore these two also are crossed out, and we end up with mu. So this is how we devised that the expectation of a Gaussian distribution is in fact the mu, the mean of this distribution. I have just noticed here one more thing. In this example, we have unfortunately somewhere on the way lost this sigma here, which you can see here. And we also actually lost at the same time the sigma squared here. And why was that happening? Because the sigma is really taken out from this equation, and it will be together, like should really have been here somehow in a step, but I skipped that step, and should have been then taken out from this sigma squared under the square root. So the two sigmas were disappearing. That's why this term has lost the sigma squared here, because of this sigma here, just that you see that. And it would also then be in this term here, but it has been already taken out in this step. Okay. Last topic, we will be explaining the variance of Gaussian distribution. What is it equal to? So we remember already that Gaussian distribution, actually variance, is equal to ex squared minus e as an expectation of x, and the same thing squared. So we already know the ex and the whole thing squared, which is a mu squared, the mean. And now we simply need to calculate what is the other part of this subtraction, the e of x squared. So what we can do here, we simply put the x squared here into this equation, but we have already also replaced the x again with the made a change of variable, that x or better to say z is equal to x minus mu divided by sigma. So we have done that, and then here in this term was in fact the x squared, but x squared is now equal to x minus therefore the x is equal to sigma z plus mu. Yeah, and that is here multiplied out squared, because the x is squared. So this is x squared after the change of variable, where we said z equals x minus mu divided by sigma. So we have, after the squared, we also multiply out this, and we obtain the term mu squared, then 2 mu sigma z, and then sigma squared z squared. Okay, And notice that we can then therefore separate this integral into these different parts which are summed up before they are multiplied with the exponential term. Again here, we will be losing this sigma squared with under square root with this, after the change of variable, this term sigma here. And now we have here the term mu squared, and we have already here 2 pi because this is this first integral part, and we know that this is an even function resulting the integral from minus infinity to square root of 2 pi. The second part is now 2 sigma and 2 mu sigma and multiplied with, as there was z here, this even function turned into an odd function, and therefore its integral was 0. So that goes out. And then here, this function is in fact again the integral of this function is again square root of 2 pi. So we have the sigma squared multiplied with the square root of 2 pi. So now the result is, so we get the 2 pi's away from both of these parts of this large integral. So this normalization factor disappears, and we end up that expectation of x squared is equal to mu squared and sigma squared. Why did we calculate the expectation of x squared? Because we want to calculate the variance. So now let's go and calculate the variance. And the variance was simply calculated as the ex squared minus of expectation of x and the whole thing squared. And so one was mu squared plus sigma squared, and the other one was also mu squared. So mu squared plus sigma squared minus mu is equal to minus mu squared is equal to sigma squared. So the variance of the Gaussian distribution is indeed the sigma squared. And now just the last thing for today is that we want to describe the so-called multivariate Gaussian distribution, d-dimensional Gaussian distribution. So far we had just single variate lobe, but now we want to look at maybe a two-dimensional Gaussian, as it is shown here, where we have two elements of this vector of continuous random variable vector x. And the normal distribution is also again characterized by a vector of mu's. And here is no longer the variance, but it is a covariance matrix of x with respect of vector x with itself, the capital sigma as a vector. And actually, sorry, not a vector, as a matrix. And now the formula for this normal distribution is similar to the exponential version of the single variate, but just slightly different. So we have here certain normalization term where we can see that there is no longer a square root, but it's actually based on the this term, this power, is dependent on the dimensionality of the Gaussian distribution. Then we have here the this covariance matrix, but it's a determinant of the covariance matrix and square root of that, as we can see here. So this is in the denominator as the normalization factor. And in the exponential factor, where we previously had the x minus mu squared divided by 2 pi sigma squared, here we have 2 sigma squared, not pi, 2 sigma squared. Here we have now this minus 1/2, so this, and then we have, instead of the sigma squared, we have the covariance matrix, and its inverse. So as if it would be somehow in the denominator, as it was the case before for the single variate Gaussian distribution. And then this term x minus mu squared is represented here in this vector form as the vector x minus vector mu. So this is a vector transpose. So we make a row vector out of this. Then we multiply it from the left with this inverse of this covariance matrix. And then we multiply it with the final column vector x minus mu. So at the end, we will have here a term which will be the argument for this exponential function. And then we can see that this multivariate Gaussian can be plotted in this way, like we can see here in this figure, where it forms a certain kind of an elliptic splats, which might be, but do not have to be, aligned with this x1 and x2 coordinate system. Now that we understand some basic properties of Gaussian distribution, let's look at the following problem. We have a set of points or xn or events which are of a continuous variable occurring independently. So at a certain instance of time, a certain value of xn is a result of a trial. And we would like to see whether we can fit a good Gaussian distribution into this set of points. And maybe not even a good Gaussian distribution, but kind of the best along the philosophy of this maximum likelihood. So what we want to do is we want to reformulate our formulation of the probability and imagine that these trials which are occurring are independent, which means that the overall probability of some value occurring is defined by the probability of the normal distribution. But as we have several of these events happening, then we have a product of these probabilities here. And this is now the probability that given a certain mean and variance, these are the outcomes of several trials. And now the question is, what would be the most likely mean and variance corresponding to these particular trials which have occurred? And for this, we use the tool which we have already been using before of the log likelihood. So we have a look at, if we look at the previous equation and put it into logarithm on both sides, we have a logarithm of this probability, and here we have the logarithm of these products of these individual Gaussian functions. Now we can also see it that this first part of the within the product is now independent of the n, which is the iterator in this product. So it's basically, we can take it out of that product, and that is n times. So here we see it was square root of so 1/2 in the exponent in the denominator, and here is not 1/2 but n half, because it is n times. We are still within this logarithm here, and the product of an exponential functions is like the exponential function, and then there is a sum within these exponential functions. Now, if we now take this further into more simplified forms, we can simplify this ln, and then we have sigma squared, which is coming from here, and then there is this exponent n half, which becomes in front of this ln sigma squared term. And as this this sigma squared and powered by n divided by 2 was in the denominator, then we have this negative value here. Another term is just ln 2 pi, kind of the residual of this normalization term. And again, we have this n half negative in front of the ln. What happens to our part with the exponential function within the logarithm function? Well, these two are, as one is the inverse of the other, we just have this argument here as a part of this equation. So this is when we perform the log likelihood. But why do we do it? Because we want to perform the maximum likelihood estimation, where we first perform we formulate the function into a logarithm, which makes a certain simplifications of our functions, especially the exponential ones, as it is the case now. But then we want to perform partial derivative with respect to one of the variables which we have in this function, and then we want to set it to 0 because we want to find the extrema, the minima, maxima, or the inflection points. Well, if we perform the partial derivative of this function, we can see that, and there is this term, there is no mu, so this will be 0. This term, there is no mu, so this will be 0. And the only function where there is mu is this one. Now, that is equal to, we have here this multiplier, which is taken out, has been taken out already from the sum, and then we perform the derivative with respect to mu of this quadratic function, which is this powered by 2 comes in the front, and then so we derive this part times the inner part, so this will be minus 1, so the result will be here minus 2. So this equation, as we have it, should be equal to 0, and then we have to reach some extreme value. Now we can reformulate this. So we have simplified it. The minus was cancelled, so were the 2's here, and now we have just this function here, and that is supposed to be equal to 0. Now, if we can split this sum into sum of xn and sum minus sum of mu's, and n times mu is n mu essentially, so this is the sum of mu's, and here we have the sum of our values of the independent events which are occurring. Please note that we got rid of this term because we multiply both sides with the reciprocal of this term, which was here still 0, and therefore we end up with the formula
that this is equal to 0. Now from that, what comes out is that mu is equal to then xn divided by this capital N, the total number of trials. And this is our maximal likelihood estimate for the mu, for the mean. Now let's have a look if we want to perform the maximum likelihood estimation for the variance, the sigma squared. We follow the same logic. So we perform the partial derivative with respect to sigma squared of this term. Now, please note that it is of sigma squared and not sigma. So here, 1 divided by sigma squared is the outcome of ln sigma squared. So this is after deriving the first term. The second term doesn't contain sigma here, therefore it's equal to 0. And the third term, we can see that we have the this is constant. This is just some kind of a multiplier of this term, and we have this term has to be derived. So out of that, this is equal then to minus 1 divided by sigma powered by 4. And this whole term now is equal to 0 because we are looking for extrema. Here we can see that we can take out the 1 divided by 2 sigma squared because it's appearing in this term and also in this term. And then we are left with, and now we are turning it a little bit around, and so this term will become first, and this will become 1 divided by sigma squared, and then the sum here, minus n, because that's the only part which was left out after taking out the 1 divided by 2 sigma squared here. And this is equal to 0. Okay, so we can again get rid of this part here. And then we have the, we put the minus n on the other side and multiply it by sigma squared so that we get rid of the sigma squared here. And we end up with having the sigma squared estimate, a maximum likelihood estimate, is equal to sum of xn minus, and now we have the maximum likelihood estimate for the mean squared, and this scaling factor 1 divided by n, because the n comes from here back to the other side. So now let's have a look at the expectation of these sigmas and mu's, so means and variances obtained from this maximum likelihood estimation from the samples. And that is the average of these. So imagine that if we have a lot of these different sample sets, then what will be the average of these? And that is here described, that now we know what is the formula for the mu, so for the mean maximum likelihood estimate. So this is this sum and divided by n, capital N. And then we can just move this estimate in such a way that the parts which some parts can go out of this argument, namely this scaling factor, and also actually the sum. So we end up with 1 divided by n sum of average values or expectation values of xn. And the expectation value of xn is in fact the mean. That's the expectation value of, because we already know that from our Gaussian distribution, and that is n times mean divided by n, which is it's the mean. So in fact, what does it say? It says that the expectation of the maximum likelihood estimate is that it will become close to the mean, and with the increasing number of trials, it will be more and more which are independently distributed and will become more and more close to the mean. Now, while that sounds like it's obvious, this is not the case for the expectation of the maximum likelihood estimate of the sigma squared of the variance. So why is this not the case? So let's have a look at this. The book doesn't cover it very deeply, but we would like to know it and understand it fully. So in similar way, we put into the expectation formula the formula for our maximum likelihood estimate of the sigma squared, but we put there inside a term which is equal to 0, and that's the term which is minus mu plus mu. Okay, so now let's have a look. If we just isolate this squared term, what is it equal to? That's equal to xn minus mu squared plus 2xn minus mu and mu minus UML. So we treat this as kind of one term, like a plus b squared, and this is the a squared plus 2ab plus b squared. So we can see here the reformulation. And then we have a look and we put it into this formula of the sum, and we see the first term here, the second term. We can take out already some parts which are not part of our, which are not subject of the xn, I mean the n iterator, and then we have the third term here. Now let's have a look at this one term, which is the xn minus mu here. So this term alone, what is it? So this is the xn minus n times mu, so this is already out of the sum, and we can see that sum of xn is like 1 divided by sum of xn, 1 divided by n times sum of xn times n, and this part here itself is equal to the maximum likelihood estimation of the mean, as we can see here, and it is then times n. So in fact, this entire term will mean that it is n times maximum likelihood estimate of mean and minus n times mean, the true mean. And we can take out the n out of these two terms. So therefore, this term, so observe that we are again reformulating this essential term, which was we will be taking the expectation of, and then we have been working on reformulating this term, which was previously just 2 mu minus mu ml, and now we realized that it is actually the other term, which was the sum, is n times mu minus mu ml. So this term becomes then 2n and mu minus mu ml squared. And then the other sum which we had was just mu minus mu ml squared in the sum, so it is n times again.
and then minus 2n plus n leaves us with the n one time here. So this is again reformulated. Now that we have simplified the terms, we are ending up with this just two terms, this sum here, and there was this minus n times mu ml minus mu squared. But we wanted to calculate the expectation of it because we were calculating the expectation of our sample variance, which is the sigma maximum likelihood estimate. So we can decompose the expectation into two terms. So the first term, and please note that we have here the scaling factor 1 divided by n to begin with, and then the second factor, which was n times mu ml minus mu squared, and the n was cancelled out with this 1 divided by n term. So we have just this form of expectation. Now we can reformulate this further by putting the expectation form here from, and this term is in fact, what is it? We can see it here. It's actually the true variance of the distribution, because we are calculating here the expectation from the true mean. And now let's have a look at the second term, which is the expectation of this term, and we can see that this is essentially the variance, and where we have not variance of x, but variance of the sample mean. So this is this term here. And then we further change this, so now we have here the sigma squared, which is now will be n times, and then 1 divided by n will be outcome of this term will be sigma squared, and then minus the variance of the sample mean, which is equal to this formulation from the previous calculation. And now we see that there is a certain term, which is this 1 divided by n, in front of our sum. And we want to take it out of the argument of the variance. And there is a known result in statistics that taking some constant multiplier out of the argument will be the constant multiplier squared times the variance of the x. And how do we get there? So here we have this formulation here, which will translate into by definition to this formulation of the variance. Now we can then reformulate this by taking here the c out of the expectation. That's what we can do, and we did it also several times before. And then we have it in both terms, so we can take it out of the squared, which will then be c squared here. And now we have it just as a multiplier within an expectation, so we can further take it out, and here we have the c squared. The multiplier which was inside is now squared outside. And that's what we will do now with the 1 divided by n. We can see it here that now the expectation of the sample variance is sigma squared, so the true variance of the distribution minus 1 divided by n squared of variance xn. And then what is this? This is now the n times, again, sigma squared, n times the variance, divided by n squared. So here we can cancel out 1n, and here
the power of 2 and putting the first term onto into the fraction will result into this result that the expectation of the sample variance is actually not the true variance, but it's biased by this term. So it's n minus 1 divided by n. And let's have a look at this in the following image here, which you can also find in the book, but in the book you will have been missing some of these dots. So this is the correct image. Now imagine that this is that all these samples, 1, 2, this is the same one here, 3, no, it's not, but so these are the other two and these are the other two. So we have different samples from the same normal distribution, and the true distribution has the mean here, is the green one, and its variance is depicted by this broad lobe of this Gaussian. Now, if we take just subset of these all samples and we perform the mean, then the mean is somehow off from the true mean. Most sometimes it's very close to the true mean because of the choice of the samples, and again sometimes it's off. But if we do expectation, if we average them, all of these, we will end up in the mean, which will be centered exactly like the true mean. But if we now have certain value from these three subsets of our sample variance, we can see that the variance is the same for all these three. And now, if we average it, we will average the same value of the variance. So the variance will be of the sample variance will be then much smaller than the true variance as it is shown in this image. That's exactly what this formula is telling us. In order to compensate for it and to have an unbiased estimate of the true variance, we can calculate our maximum likelihood estimate of the variance here and then scale it up with the fraction which is reciprocal to the previous fraction in order to get the a little slightly higher value for the unbiased estimate of the variance of the distribution. And this can be also reformulated into this term here, as we will have for this term, we will have 1 divided by n of this formulation. So obviously the numerators n and the denominators n will be cancelled out, and this is the final formula for an unbiased estimate of variance of a distribution from its samples. Please also note that with increasing number of samples taken out of the distribution, this term will be increasingly more and more closer to 1. So towards the end, the difference between the maximum likelihood estimation of variance, which is the sample variance, and the true variance will be rather negligible. But for small counts, the difference will be substantial, as we also have seen in the figure. Now, let's have a look at evaluating the regression which we had before, but with assuming that we have a Gaussian distribution around our mean, that we have a certain function which is noisy, and this noise is following a Gaussian distribution. This Gaussian distribution is having a mean around at the function which we are looking for,
and it has an unknown variance. Now, unknown variance, reciprocal variance is precision, and it's termed by the term beta here. So we see that we are looking here for a function which has for one x and its probability of corresponding to particular t is subject of the actual function which we are looking at, the y function, and then the unknown variance or precision. So, and this then follows the normal distribution where given a y which is of a certain, which has a sample x and known weights w, and given the variance which is the beta powered by -1 or reciprocal of beta. So, and as we have our terms, our samples independently taken, we have again this independence results into a product. So the overall probability that for a given set of all these samples from x getting the value t is the product of these individual probabilities following this normal distribution. And let's have a look how we then can calculate the function y, or the better to say the weights w, the weight vector, and the precision or the variance. So now we will be searching again for the mean and also for the variance of this normal distribution given as the product of these normal distributions. However, now our mean is actually given by the function y, and that one is essentially determined by the weights w. So we will be with that we will be looking for the vector w, and which will then determine as the mean at the given position for each xn, and then we will be looking for the variance, which is the reciprocal of precision, or the precision is the reciprocal of the variance. Therefore, our formulation will be slightly different because we have here this beta here, and previously we had the sigma squared. Previously in the denominator, the sigma squared was powered by n½ but now the sigma squared is no longer in the denominator, but the beta is in the numerator and is powered by n½ So that's one thing that's slightly different, and that will lead to some change of signs. And the second thing is that instead of performing the maximum likelihood estimation, we are performing the log likelihood, but a negative one, and maximizing the log likelihood is the same as minimizing the negative log likelihood. So, and then therefore we are searching for the w, which is subject of this finding the best minimal value of this whole argument. Now, the negative value here has turned this previously negative value of this term to plus, and this term was also negative, now it's positive. This term remains negative because we have also now, this is no longer, was no longer taken out of the denominator, so it would be positive because it was in the numerator, but by multiplying with the -1, it's negative again. So this is our final term. Now, we will not follow the traditional way of putting the derivative of with respect to w, and then we have making it equal to 0. We just reformulated that we are looking for the argument of this part, because that's the only part which is dependent on w, should lead to overall smallest value. And whether we will do this with the derivatives or not, what we can see here that just by assuming that the noise is a Gaussian distribution, we can see that the result of this minimization is the same outcome as when we were looking for this was the error term before, which we were using for finding the right polynomials, which would be approximating our sample points from a couple of lectures before. Now let's have a look at calculating the variance. So now with that method we can calculate the vector of W weights. But now for the variance or the reciprocal of it, the precision, we have here the following formula. So we have the logarithm here as we had it on the previous slide. And now we perform the derivative with respect to beta, and here we have the term ln beta is equal to 1 divided by beta after when derived, and here we see that our beta half is just the beta is replaced by 1 after the derivation. And reformulating this is whole equal to 0, and when we reformulate this a little bit, we realize that actually the variance can be formulated as the variance with the mean being the y function itself. So with this, we have generated a so-called predictive distribution, because we have now we have calculated the w vector with the maximum likelihood estimation and the beta with the maximum likelihood estimation, and we can put it into our normal distribution parameters. So we obtain the y function given the w vector and the variance or the beta obtained by the maximum likelihood estimation. So given nx, we will then have a certain probability where our t will be, what will be the probability distribution for the t. So we will have not only specifying specific t, but a probability distribution where the t is. So far, we have calculated the maximum likelihood estimation for the weights vector W and for the given for the precision or the standard deviation. Now, we would like to introduce a prior distribution for the weights vector. Here, we would like to define that the weights are somehow all centered around the mean 0, and their deviation from the mean is characterized by this covariance matrix, which is an identity matrix multiplied with a scalar, effectively creating a diagonal matrix with the diagonal terms a powered by -1 along the diagonal. So
the A is here again a precision characterization, while here this reciprocal takes the form of the standard of the variance for the scalar for this covariance matrix. Now let's have a look at what does this mean for multivariate Gaussian. Here we can see that the standard formulation, and we see this term here is defining us how many what is actually the degree of our polynomial function, which is characterized by these weights W. So this m plus 1 m is the degree plus 1 is the amount of the various powers of W, or powers of the x, the input. We can see here is the determinant of our covariance matrix, a square root of that, and here we can recognize the exponential function, where we see that here is the characterization of the W distance from the mean, and here is the covariance matrix inverted. Now, one aspect we can have a look at is that what happens to this term after we calculate the determinant. Imagine that we have a determinant of this matrix. So what happens if we have just the values on the diagonal? Actually, the determinant will become a product of all the elements along the diagonal, which means that we will have a powered by minus 1, and this will be powered by m plus 1. So this will be a powered by minus 1 times times m plus 1, and then the square root of that. Well, that actually brings our alpha with this negative exponent. You can put it into the numerator and make a common term together with the pi, with the pi, so that we have the common exponent m plus 1 divided by 2 for the alpha in the numerator and 2 pi in the denominator. So this is how we reformulated this term. Now, after, and the second part is the exponential functions of this product, where we can see that we have here the alpha can be taken out, and it's part of this this scaling factor here. While we have for the weights, as we have the mean is 0, we have here the product of the matrices and effectively forming a dot product of these weights. And the prior we can put together with the likelihood function here in order to create a posterior distribution, which takes into account both the prior and also the likelihood function. Now we can evaluate this and estimate both the beta term and also the weights W with a approach which is called maximum posterior, where we multiply these two probability distributions and perform a logarithm, and we can see, or actually a negative logarithm, and we can see that the outcome is then a sum of these two terms, or subtraction. So here we can see the already familiar part of our likelihood function, which looks exactly like it looked in the previous case. And here is our new part, which comes from the prior. The prior, which tells that the mean for W should be 0, and it should have some given
variance characterized, or covariance matrix characterized by this alpha. So we can see that the exponent was coming into the front after the logarithm. We have this a divided by 2 pi within the logarithm, and the next part is the exponent coming from the exponential part of this normal distribution function. So, and if we now are observing only the parts which are dependent or characterized by the vector W, we have, and which is important for the finding the minimum of this negative log likelihood, we can see that this is only the terms which are the sum, where we can see the sum of square differences from the mean of which is characterized by the function y, and then this term with the dot product of the weights w. So this is actually the term which we are trying to minimize, and this term, as it is minimized, we recognize here that this is the sum of square differences error function, and here, in fact, is the regularization term, which was trying to create as small w's as possible as a part of this overall error function minimization. So we can see that the maximum posterior with this prior we have defined is actually related or corresponding even to this least squares with regularizer. Finally, let's spend a few words on characterization of a full Bayesian treatment for this curve fitting problem. As in the previous cases, we have been analyzing and devising the predictive distribution of where our target values are given a certain x based on the values x and t from the training. However, with our minimization approaches, either maximum likelihood estimation or the maximum posterior, we have in both cases devised the kind of the best vector of the W's, which are our multipliers in a certain polynomial function, which is fitting our points. Now, so we actually did so-called point estimate of this weight vector instead of taking into consideration all possible weight vectors and their associated probabilities. So the Bayesian curve fitting will in fact consist of a systematic multiplication and summation of various probabilities associated with a certain vector W. So we can see that here in this formula, where we have a Bayesian treatment where our input information is the set of training data, the vector x, or the vector associated with the vector t, and then the characterization of alpha and beta, alpha coming from the prior, from the slide before, and then beta being the precision. Now, for the moment, these are also fixed and not being predicted. And then our probability distribution is characterizing the probability associated with the various positions or values of the t. And we obtain it by this integral of the maximum posterior probability here, which measures the probability of a certain vector of weights. So this is an integral over all possible vectors W. So, and each vector W is associated with a certain probability distribution. So for some, admittedly, it will be very low probability that the weights are corresponding to those values, but for some, especially those which are associated with the maximum posterior, will be given a higher probability. And that is multiplied with the second term, which is characterizing the likelihood that given that particular weight vector and the precision and a given x scalar value, what is the probability distribution of a given t. So that is now the product which forms as the full Bayesian treatment. It turns out that this is again would be a normal distribution with a mean and variance as some functions of the new value of x for which we are searching for the t, or predicting the probability associated with a given t. You can see this function, and we will not go more into details of this function mx and s square x for mean and variance at this point, but you can see that this predictive distribution is now associated with a normal distribution around the mean, where the mx is now characterizing this function here, which was the y x of x before, and s square x is characterizing the variance of this function. Let's discuss the various characterizations of our prediction task, whether it is about the regression or classification. In case of the polynomial curve fitting, we have seen that just for the sum of square differences, we could devise a certain power of prediction given and one characterization was the degree of the polynomial m. So for low degree polynomials, the predictive power was maybe not as powerful as for the degree of 3 for cubic polynomials. But we have also seen that if we are having a very high value of m, like the amount of samples available -1, then we will have the problem with overfitting. So m is one parameter. In the regularized least squares, we had the parameter lambda that would be controlling how much is actually the regularization influencing the outcome of this minimization approach. So both of these parameters are somehow expected to be given for the task of finding the appropriate weights for the model. And these parameters should be chosen such that we have the best predictive performance. Now, one thing which we can do in case we have, let's say, unlimited amount of data for some scenario, that we can train several models instead of just one on a range of values, and then so not all the training data is associated with each model, but each model has different set of that training data randomly chosen, and then we can set a different value of m and lambda in this case, and we will be able to see which model is then performing the best. And the performing the best will be characterized on yet another set of data, which we will call the validation set. So we have the training set, and then we will have many training sets from which we will have the calculate the models, and each model with different parameters or hyperparameters. And then we have the validation set on which we are evaluating the actual predictive performance. However, we can do this several times, and in order to not to overfit to the validation set, we also want to perform the final test of our performance on a test which the process of finding the right weight values and hyperparameters has never seen, and that would be the test set. So we will typically partition our data into three sets: the training set, the largest one, a validation set, and then the test set. And the training should be only performed on the training set or training sets. The hyperparameter tuning is determined by using the validation set, and then the final outcome and measure of the predictive performance is evaluated by the test set. If we have a set of data, then what we could perhaps do for finding the right model is the method of cross-validation. In the cross-validation, we will partition our data set into various subsets, and then we will use part of these subsets for training and one subset for the validation. So here we can see in these graphics the so-called S-fold cross-validation, which uses the S-1 divided by S data for each model training, and the performance is then assessed by the entire data, because the last part of the training set is used for the validation. So this S-fold cross-validation is training S number of models, so this will be 4 in this case, and it partitions the training data or the data into S partitions, and then one of these partitions in each model training, a different one, is used for the validation, and another one partitions, the white ones in this case, are used for training. And each of these models is trained with different hyperparameters. This has, unfortunately, the property that the training time will increase S-fold. So if we have if the training time needs to be limited, then this technique will not be ideal. In case of we have not just a little bit of data, in dozens, then we can also use the variation of the S-fold cross-validation, which is called leave one out, where the n-1 data elements are used for training, and the last element is used for the validation. And in each run, we have the different element which is used then for the validation. We can also see that with running S-fold cross-validation, we can only check for S parameters. So the choice of parameters would be need to be done very wisely so that we can gain the best possible performance from training just a discrete set of or a limited amount of different models. Another aspect of within this introductory part is to cover is the so-called curse of dimensionality. Often the the properties and the characteristic we see and understand intuitively around us in lower dimensional cases might not be that intuitive in higher dimensional spaces. So, for example, look at this simple case of the type of classification. There is some kind of a case where we have some kind of a flow. Here are various data points. We can see the blue points, the red points, the green points over here in the picture. And we are interested in this one, the value of classification of this one value x within this two-dimensional plot of actually multi-dimensional, 12-dimensional simulation case of a flow of oil. Now, these RGB codes for blue, red, and green are encoding homogeneous, annular, and laminar flow categories. The question is, for this X, what type of flow category do we classify this point into? And a good way to do this might seem to look at what values are in its neighborhood. So for example, here we can see that there is just nearby is a red point, some green points are also nearby, and the blue points seem to be quite far away, so that seems to be unlikely category. So one, we could look at nearest neighbor, for example, or we can classify these cells here into somehow a type of flow which is dominating in that cell, so discrete cells here, discrete borders, and in that case, as we see in this cell, that will be the I assume the R will be the annular flow will be dominating this cell, and our X can be then categorized by into this category. However, imagine that we do not have only two-dimensional case, but we have a multi-dimensional case, like 12-dimensional, the whole data set, and then this uniform subdivision might not seem to be that easy to perform anymore, because we simply will find out that with increasing dimensionality, we will be also having a problem that less and less points are in such cells in higher dimensions. So let's have a look here that we have this is one-dimensional case, this is two-dimensional case, three-dimensional case, and we have a certain, some several hundreds or hundred set of points, which will be making very dense representation in one dimension. In two dimensions, they will be still reasonably dense to categorize, but in dimension 3 we can see that it will be already they will become more and more sparse. And for 12 dimensions, we will probably have only sometimes we will have cells in 12 dimensions where there will be no single element in that cell, and that will mean that it will be very hard to classify what type of flow is in that cell. So so the data would need to grow exponentially with each increasing dimension, so that we are able to keep the same predictive performance by the number of elements in the cell. So, and this is an illusory situation, because we will soon not have enough data for these complex multidimensional scenarios. If we look at the polynomial curve fitting example, we can also see that the number of weights which we will have to devise will be growing also with the dimensionality. And we can see here that for the polynomial of order 3, we generally need, so we have x equals 3 in 3 dimensions. We have weights associated with x, and then we have we have weights associated with x powered by 0, x powered by 1, x powered by 2, and x powered by 3. So for all these coordinates, we will have a different weights associated, and generally the number of weights which we would need would grow with the for polynomial order m in d dimensions according to the power law. No, so not exponentially, but according to the power law. And so increasing the polynomial order will be the exponent, and the dimensionality will be the base here. So the power law will still quickly grow our requirements for the data, and also for the number of weights. Let's have another look at the dimensionality aspect. So imagine, and this will show us how unintuitive the high dimensional spaces might be. Let's have a look at the sphere case, and let's imagine that we have a sphere, and this sphere we are measuring some kind of outer shell of the volume of that sphere, and we want to know what is the fraction of that volume which is concentrated in that sphere of various dimensions. So we have a one-dimensional sphere which is very linear, so this is really just a line. And then we have a two-dimensional sphere, and we can see that it has the shell. So here the shell of the volume is characterized by a certain epsilon, and this is the volume fraction. So if the epsilon of the unit sphere is 0.2, so the volume between the radius 0.8 and 1 is being measured as the fraction to the entire volume. And we can see that this is this value. But if we now are not interested in two-dimensional sphere, meaning a circle, but in 20-dimensional sphere, then we can see that almost all the volume is already concentrated in that shell, outer shell, and the inner core of the sphere is not having almost any volume. So, and let's have a look how we can calculate that. So here we have the volume of our sphere, and the entire volume, and then here we have the volume of the shell and the fraction to the entire volume. Now the volume of the shell and of the smaller this is the entire volume, and this is the volume of the small core of this sphere, and this will create as the volume of the shell and to the fraction of the entire volume. So how can we calculate the volume? The volume is a function of some constant for a particular dimension times the radius powered by d. And with that we can quickly calculate that this constant is both in this term and also in this term, and also in this term for a particular dimension. And what it's differing is only the r powered by d, where the RT will be taken out from both the numerator and the denominator, and will be cancelled out, and we will be left out with a formula which is characterizing as the fraction of the volume which is in the outer shell, characterized by the epsilon. What is the fraction of the volume to the entire volume? And we can see that in 20 dimensions we already are having almost the entire volume in this outer shell, and in the inner core there is almost nothing. Similarly, if we look at the Gaussian distributions in higher dimensions, we can see that the probability mass distribution is shifting from the zero away from the origin with increasing dimensionality. We can interpret this as observing a Gaussian and having a look at a certain band of the Gaussian from like imagine in 2 dimensions the Gaussian is kind of split, and then we have a kind of a ring around the mean of the Gaussian, and we are summing up the probability of that ring. And we can see that with increasing the dimensionality, the highest probability will shift of this kind of a ring will shift from the center of the Gaussian, which is centered around mean for dimension 1, and also very close to the center for the dimension 2, to further away for the dimension 20. So this ring of highest probabilities will be at some radius of 2 distance from the mean of this Gaussian distribution. So this is on one hand sounds very hopeless, that we do not have effective means to treat this multiple dimensionality, and with machine learning we are trying to attempting to solve problems which are admittedly very complex, but we can see that sometimes even in cases of high dimensionality the effective solution can be found with a smaller number of parameters. So, and typically our solution lies on a manifold, nonlinear manifold, which is embedded in a multidimensional space. And the second aspect is that often our data is smooth, and so the changes are not abrupt in the phenomenon we are observing, and therefore if we have known certain variables in some places, the chances that the variables, the outcome target values in the places, input values which we didn't sample, might be similar to those nearby. So if we have a look at one example, like imagine a conveyor belt with which has many pixels, which 512 times 12 pixels, maybe of 1 byte bit depth, then this will be our input vector, but we are only interested in the position and rotation of a certain object within this image. Then we will really have just 3 degrees of freedom, 2 for position and 1 for the rotation. And if we will have so this set of images live on a 3-dimensional nonlinear manifold embedded within this high-dimensional 512 times 512 space. Now that we are equipped with some basics of a probability theory, we understand that the input and output can be characterized by the probability theory. Recall, for example, we would have an input vector, which is the shades of pixels characterizing the image of a freehand digit, and the output vector will be the set of possible digits which this image corresponds to. So with the probability theory, we will establish a joint distribution of which will characterize of the probability of co-occurrence, the input and output vector and their particular values. So this would mean that we have a certain probability in the case of the digits that a certain image could be, let's say, a number 8. So with a certain probability, maybe it could be number 6 with also a certain probability. And but at some point, we need to decide on what is that, into which class do we want to put that particular input vector. So while the probability theory is concerned primarily with establishing this channel between the input vectors and output vectors through this joint probability distribution, the decision theory is concerned with determining, based on the probability theory, based on the joint probability, is concerned with determining the optimal value of our output vector so that we can perform a specific action, like, for example, understand the digit. Let's have a look at another example besides the example of the digits. It's a similar one because it also involves images. In cancer diagnosis, for example, for maybe lungs or mammography for breast cancer, there is often an X-ray taken. It is an image which has an input vector of pixel values, and the output variable is the presence of a cancer, where we could say the presence of cancer is C1, the class 1, which is associated with the T value 0, or it is a C2, which means an absence of a cancer, and the T is equal to 1. So with during the training process, based on some supervision from known outcome from images of cancerous tissue and non-cancerous tissue, which are known, we can establish the joint distribution of PCK, which will define an uncertainty given a certain image. What is the probability of a cancer in that image? And this characterization is called the inference. And then the next step is the decision to decide, is there a cancer or is there not? So we need to somehow binarize this, smooth probability between a cancer and non-cancer, and decide for one of these two. And this will then influence the treatment of the patient. So let's see on this example how the probabilities play a role in making a decision. Imagine that we have a new image, X-ray image, taken X of a patient, and then we are basically, based on this image, interested, given the image, what is the probability of the person having a cancer, or what is the probability of this patient not having a cancer. And this information can be obtained from the Bayes theorem, which is formulated here, and we can see that all these quantities are somehow obtained from the joint distribution by either marginalizing or conditioning the joint probability. Now, for example, the PCK can be considered as the prior characterizing the probability of a cancer of a patient before the image was taken. So this might be based on some populational statistics in that particular country or in that city of a likelihood of a cancer in the population. It might be associated with some family records of that particular patient that would make it more or less likely of having a cancer. The posterior is then defining what is the probability of the uh, cancer or not cancer given an image, taking into account, of course, also the prior. Logically, if we obtain some posterior probability of cancer or not cancer, it seems that the most natural choice, if we need to make a decision, would be to pick the value which has a higher probability. And this intuition is in fact correct. For making a decision, we need to define a certain rule how we decide on whether a person has a cancer or doesn't have a cancer. And this rule will be forming certain decision regions. So imagine we have the probability distribution of which is a joint probability of a random variable x and c1, and here is the joint distribution of x and c2, and we can see that there is a region R2, and from which, if for a certain x, there will be considered an absence of a cancer if the x is falls into the region R2, meaning it is bigger or equal to the x hat. And then we have the region R1, which is associated with the decision of a presence of a cancer. And now let's observe this drawing again. So we have these two different probability distributions of a presence and absence of a cancer, and we have also certain errors associated with making a certain choice. Imagine that we can arbitrarily move this x hat, and we are actually trying to minimize making a mistake. So how do we characterize making a mistake? Making a mistake is can be characterized, the probability of a mistake is basically a sum of probability of x belonging to the region 1, and despite that, the person is not having a cancer. So in fact, because there is a certain non-zero probability of the C2. So we can see, in fact, in some areas that probability of not having a cancer is even higher within the region of C1. And then we have the second part of the mistake, which is the probability associated with X being part of this region, but despite that fact, the person would have a cancer. And that is somehow characterized by this part in this drawing, because we can still see that there is a non-zero probability within this region R2 for person having a cancer. So that mistake is somehow associated with this part. And we can see here that these are basically characterized by these integrals. So here we have one integral over the area R1, where for all the events, or for all the, in case of continuum, for the entire interval, where the C2 probability of Pxc2 is non-zero within the interval of R1 and plus the integral within the interval for xr2 of the probability of person having a cancer in the region R2, which is this area. So if we sum up this area and these two areas, that is the probability of us making a mistake in the decision if we have decided that x hat has this particular value. Now let's try to move this x hat a little bit and see what would be happening. So if we would be moving this x hat on, let's say, this way to the right, we will be having the same mistake, like the green area and the blue area in sum will be the same, but we will have an increase in this red area. So in fact, we will be increasing the mistake. If we will be moving the x hat in the different direction, like towards this x0, we will see that the probability of a mistake, the green and blue will not change in area, but we will get gradually smaller and smaller value of the red until for the value x equals zeros, it will entirely disappear. And that leads us to the observation that if we are moving the x hat to the value of x0, we will have overall the probability of making a mistake being minimal. And in fact, what we can observe here, this is exactly the area where the probability of a presence of a cancer is becoming higher than the probability of not having a cancer, and overall. So at this point, this is the point for these two distributions where we will minimize the mistake, and that also leads to the intuitive observation that in case of posterior probabilities, we should always pick the one which has the higher probability out of the two for making the decision. The probability of correctness we can calculate in a similar way as the probability of a mistake. It's simply the probability of the x from the region K being associated with the classification CK. And we have here this this could be reformulated to this set of discrete classes of decisions, or that's in our case presence or absence of a cancer, and then we have the integral over that region RK, and just to understand what is the area of the correct classification. So in this graph, the correct classification will be for the RK. R1 is the area of the, if we always are correctly classifying all the values until the on this whole interval here. So in fact, it will correspond to the integral under the curve of our probability distribution from here to here. And for the correctness is depicted also here in this part where we have the probability of correct assignment associated with the area under curve of the probability of the absence of a cancer from the point X hat or for the entire region R2. So now we have learned how to minimize a misclassification. However, misclassification might not be as an ideal way how to minimize the problem or decision making in a given situation. Sometimes making one type of mistake is very different from making another type of mistake. So imagine, that's why we have here this cancer treatment or cancer diagnosis scenario where this becomes very visible. Imagine that we make a one type of mistake where we diagnose a patient who doesn't have a cancer, who is healthy, that he or she has a cancer. As a result, this person experiences psychological discomfort and, in the worst case, is given even some medication which is unnecessarily given and causes additional discomfort to the patient. In the other case, in the second mistake, where the patient will be given an diagnosis that is healthy, but in fact that patient has a cancer, and as a consequence of decision is not treated, and is ending up in the fatal event of death, that mistake is much more severe. So in that case, making simply and minimizing the misclassification would not be a satisfactory measure for these two cases, as these two misclassifications are not symmetric, they are not on the same scale. Therefore, we can introduce the concept of loss or cost or utility functions that would be helping us to find to better characterize the mistakes we are making. This the design of these loss functions can add this needed complexity, so that at the end we will make maybe more mistakes of the first kind than mistakes of the second kind, which should be avoided at all in nearly all cases. So, and then the optimal solution would be to minimize the overall loss. The concept of loss can be well understood when observing this particular matrix. We could also use the term cost for this very moment. So you can see on this matrix that it has diagonal values which are associated with a correct diagnosis. So we make a decision that the person has a cancer when he or she in fact has a cancer, and we make a decision where the person is healthy when the person in fact is healthy. So, and this is associated with the cost of 0. So we didn't incur any cost, we didn't make any mistake. On the other hand, on the anti-diagonal, we see some costs associated with the mistakes. And when we perform the first categorization, when a person is in fact healthy, but is diagnosed as having a cancer, we have a cost of 1, while in the other case, where the person is having a cancer but is diagnosed as healthy, is much associated with much higher cost. And then we will be using this loss matrix in order to amplifying the mistakes which are of a much severe consequence, and overall we would like to then minimize the overall cost or overall loss. So, however, we do not really know the true class of an unknown imaging. So we do not really have a clear understanding of that. What we only have is the joint distribution, which characterizes the uncertainty between the two random variables of the input image and the classes of having a cancer or absence of a cancer. So our goal is to minimize the overall loss or the average loss, and we do it by choosing the regions Rj such so that the average loss is minimal. For that, we are using the joint probability distribution weighted by the entries of the loss function. So here we can see that we are performing a weighted calculation of the area, and the weight is always associated. It's coming from the loss matrix. So we can see that we have one iterator K, which goes over all the classifications. And then we have the iterator J, which goes through the two regions which we have defined. So for a region J, we will be calculating, let's start for our case, particular case, how this will run. So first the K is equal to the presence of cancer, that's the category CK, C1, and then we are in the region R1, which is associated with the cancer. The law we can calculate the weighted probability, however, this weight is 0 in that case. Then we are moving to the other region with this iterator and calculate the loss, which is the error associated with the category is so the patient has a cancer. However, it is in the region of being healthy, and that is associated with this heavy cost of 1,000, and we are calculating the integral of that weighted by this very heavy loss. And then the K increments to 1, so we are in the second part of the matrix. For the first region, so we are again making an weighted area of this region, which means this is the mistake we are making when we are categorizing a healthy patient as having a cancer. And that is associated with this weight 1, and we are calculating the probability of being that the case as an area under that particular probability distribution. So the question is now, what will be the setting of these regions so that we will have the overall minimal average loss? It actually corresponds to assigning each x to a class J for which this sum term is a minimal. And this sum term is for a class J which is our decision, is a sum of not making a mistake. So this is the loss is 0, and then the corresponding probability to it, and then plus the loss when making a mistake and the associated probability with it. That gives us a certain value for choosing one class J. Then we choose the other class J, and then we again calculate this term for again having the right decision and the wrong decision, and we calculate the final sum. And if we choose the minimum out of these two, that would lead and associate the x with the particular class J and then to the region J, that will overall lead to the minimal loss. Observe here that we have also at this point changed here that this is no longer a joint probability, because we are in fact the joint probability, as we know, can be calculated by the conditional probability of ck given a certain x times the probability of x. Now the probability of x is in both cases the same, and therefore we don't need it for making this sum, and therefore we are just interested in the posterior distribution given what is the probability of ck given a certain image x. We can see here how these two posterior distributions might look like, where we see here a very high probability of a cancer given a certain image, and then we are increasingly, when the x is changing, having increasing of the probability of the not absence of a cancer of a healthy patient. Now, mistakes are typically happening under the unity. Typically, they would be appearing when we are in the region where we are less certain with the posterior probability distribution. And an option which is called the so-called reject option is to say that everything below a certain value of a probability will be not will the decision will not be made. Imagine that we have, for example, an automated decision making, and we only want to make the automated decision making for clear cases which are very close to one, and for cases where this probability of a certain value is dropping, we will be associating it with making a no decision, and maybe deferring the decision to manual observation by a clinician. So this is called the reject option. At the beginning, we have divided the process of interpretation or classification into two stages: the inference stage and the decision stage. Now, there are in fact several various complexities how we can reach to a decision. So the most complex one is to create so-called generative models, where we learn the inference as we see it here, the posterior distribution given a certain training set and then a certain prior, and we normalize the we calculate the probability of x as the sum of all the likelihood and prior for all categories. So with that, we calculate the posterior, and then for generative models, we also create we model explicitly or implicitly the joint distribution of inputs and outputs. That means that we are actually able to, given a certain probability of a cancer, we can actually generate an image which would correspond to it. So we can both, given a certain classification, we can generate an image, and given a certain image, we can generate classification. So those are so-called generative models, which allow for generating synthetic data. And this is the most demanding type of models, which model the joint distribution. The second category of models are the discriminative models that only learn the posterior distribution and then use the decision theory and regions definition to assign the X to one of these two classes. And the third option is to not even learn the conditional probability distribution, but to in fact directly find some specific discriminant function that maps X onto a label, and there is no probability associated with it. Here on these images, you can see that there is a certain structure of the probability distributions of X given a certain condition, so which has quite some structure. So this is what we would have in the generative modeling case. However, because we will be modeling a continuum out of this set of discrete samples of images, and then we can sample that continuum as well and obtain synthetic images. If we only are interested in classification, you can see that this posterior has much simpler structure. We do not see the structure shown in this plot being reflected on the posterior distribution. The posterior distribution is much simpler, and we can see how a decision boundary could be set. What are the advantages or disadvantages of these various models? So clearly, the generative model is the most complex and computationally expensive, and can be used also for generating new input vectors. However, in contrast, the discriminative models cannot do it, but they can still perform the classification. And even if we would have a change of the loss function for some reason, this can be adapted into finding the regions so that the loss is overall minimal. If we will have only the discriminant function and the losses will be changing for some reason, this discriminant function will not be able to be accommodated, and the whole decision making would need to be calculated from scratch. While it might look tempting to convert the whole decision making into just a simple discriminant function, given a certain region, it's this or that, and not having the posterior probabilities and the discriminative model available anymore, it will have then disadvantages, like in the mentioned case of when the loss matrix will change, or also if we will have new data coming, and if we would have the posterior probability, that one would be possible to update. Also, if we have the posterior probabilities available, then we can still make use of the reject option, which is giving us a certain, which is conditioned by a certain conditional probability value. Also, if we have a certain class priors which we would need to compensate. Imagine in practical scenario, if we are taking images from a certain hospital, then most of the imaging will probably be, most likely be from a population will be healthy. And only few of these training data will be actually containing the cancerous tissue and will be classified as having a cancer. And this actually already creates a bias in the training set, because if we will have just 1% of this pathological cases in the data, then even having a classifier which always selects healthy will lead into 99% of precision. So this is clearly not good to have such a bias in the data, and we would need to actually train the classifier on an equal set of healthy and pathological cases. And once we calculate our posterior based on these classes, then we can actually divide the posterior by the distribution of the images or the training data we had for the healthy and for the pathological cases, and then we can multiply it again by the populational distribution of what would we expect as would be in that given group of people which we will be evaluating the images from. So these compensating for class priors will be also a possibility using this posterior distribution. Also, if we have different models, like if we have one model for where we have a classification to healthy or pathological from X-ray images, and another one from the blood samples, and we can treat these two training sets, to these two different modalities, as being independent random variables. That means that we can define a certain conditional independence, which is the so-called naive bias model, where given a certain class, given a certain presence or absence of the cancer, we can see what is the probability of the particular image and a particular blood sample. And that is equal to as they are independent random variables, this conditional independence means that this is equal to the product of the conditional probability of a given CK of a particular image and the probability of a given CK of a particular blood sample. So, and out of that, out of this conditional independence, we could calculate the posterior of these two random variables, which is proportional to the likelihood function and the prior, and that is in fact this is equal to the product. This function is equal to the product of these two functions, these likelihood functions, where we know that this will create us the posterior of given a certain random variable xb, what is the probability of a certain certain diagnosis, and then so this product forms us this term, and for this term in fact would be equal to the so this product times another ck would be equal to this term, which means that this term can be replaced by the this posterior with respect to xi divided by the probability of the marginal probability of the certain class category. So this was another example what a discriminative model, or for that matter also the generative model, will offer us in addition, in contrast to only having the discriminant function available. So far, we have been talking about the loss function for classification. Now let's turn to the discussion on loss functions for regression. That would lead to similar cases as this polynomial curve fitting problem, where we were trying to find for a given set of input vector x and the output target vector t, the function which maps the x to t. And for creating a loss function, we would like to observe what is the average loss for the which is weighted by the joint probability of pxt. So here we can see that the loss is again acting as a weight to the joint probability distribution. A good choice for loss could be, for example, the sum of squared differences, which we have been already talking about before. Now we can see that this loss is then we see here that we have the term yxt, and our strategy now will be to again perform the derivative and then find the extreme values by setting the derivative to 0. But in this case, we will be dealing with the functional derivative of the function y by setting the value x stationary. So this leads to that we are performing the derivative with respect to the function y of x, and this leads to the fact that this square term is then derived. We have then 2 here, and then the times 1, because if we derive what is inside of the square. So we end up in this formulation where the yx minus t times the joint probability dt is equal to 0. And we are performing this for a fixed x, so that's why the derivative with respect to x is not present in this formula. So we solve it only for a given for a given x which is fixed. Now this formulation, we can get rid of the 2, and then we can also divide this we can put it on both sides, where the yx p at xt dt is equal to then the t times the joint distribution dt both in the integral. Now in this side, we can take out both terms out of the integral by marginalizing this joint distribution. When we are integrating the joint distribution with respect to the one of the variable, we are getting the marginal probability of the other variable, and the yx term is actually not dependent on t. So we take this this is the result of the integration, and on the right hand side we have the same term where we see that the joint distribution is multiplied by the t. Then for expressing the yx, we can see that we have the following logical formula, which then leads to the formula of so this probability distribution and this probability distribution will create us the conditional probability distribution of given x with respect for t, and this we can see is in fact the expected value for t given a certain x. And we can see this result graphically as well, that the yx is the best guess for yx to be to have the smallest loss in this squared loss case is that if we are having the expected value, so the mean of the given value x at the given x value x0, and for the distribution of t, we will be choosing the mean value or the expected value. And this, if we do this for all the x, at the end, we will then recover the function yx, which is always at each position x, the mean of this distribution of the probability distribution of t given a certain x. Now, also in the case of continuous variables, we also have the same considerations when we are thinking of generative modeling or discriminative modeling, discriminative models, or the discriminant function. The same aspects apply both in terms of complexity and also in terms of opportunities, what we can do if we have either the full joint distribution or we have the conditional posterior or we only reduce the decision making on a certain discriminant function and forget about the probability distribution altogether. Last comment, the loss functions for regression, the some square differences was only one way to express the loss. There are many other losses possible, and there are many losses possible even with the family of we would call an L2 norm. We have L1 norm where the exponent will be 0, and it will be, this difference will be in absolute values, and we have other norms which are characterized by the value of the exponent of this difference. Now let's continue discussion about another theory which is important for machine learning, and that is the information theory. So information theory is concerned with understanding what is the information associated with a certain random variable x. And intuitively, we can somehow understand that if we have a random variable x, meaning that x has various values, and these values are occurring at a certain probabilities, then if we have an high likelihood, meaning high probability that a certain value will be reached by the random variable x, probably this will not be lead to much of a surprise. If we always have like a probability of certain digits occurring, but the digit 0 will be with 70% of probability, when we will see 0, we will not be very surprised. In contrast to if we have an event occurring with a low probability, with decreasing probability, the level of surprise is increasing. If suddenly some value shows up which we would not expect, that leads to a surprise, to new information and valued information. So it turns out that the information value is intuitively reciprocal to the probability, and the higher the probability, the lower the information, and the lower the probability, the higher the information. At the same time, we have other properties which are associated with a certain information quantity. So let's call the information quantity now hx, which we know that it depends reciprocally to the probability. And at the same time, we have two following considerations. Imagine that we have two independent events happening and both associated with a certain information content. Well, if these are two independent and we have two sources of information, their occurrence can be expressed as a sum of the information, both independent informations. At the same time, what holds as the information is associated with probability, that the probability of the joint occurrence of these two events is equal to the product of the individual probabilities. So therefore, we see that we have a certain, if we are looking for a function which is quantifying the information content, it needs to lead for independent events to a sum of information, while their probabilities are then, if they are independent, the joint probability is a product of the individual probabilities of these random variables. So if the h depends on the probability x, then we see here that the product is here px/py. If we put this argument to the hxy, that this is the argument for hxy, then in order to achieve a plus out of the product here, the only function family which was satisfied is actually the logarithm. So for logarithm, observe that if we have the product of, if we have the joint probability in an argument which leads to the product of the two, then we can reformulate it into individual logarithms and the sum of these two. So and also we can see that this logarithm is a negative logarithm. So if we want to put it back into this argument, it will be px powered by -1, so the reciprocal of the probability. That's why the information content is the negative log of the probability distribution. Now here we would be using the basis of 2 for a short moment, just to characterize the probability so the information content from the perspective of digits, binary digits. So the information content is then measured in a binary digits called bits. And closely associated with the information content is the measure called the entropy in the information theory, which is the quantity which measures the average amount of information which is coming from a certain random variable. So the average amount of information is then calculated as an expectation where we have the function hx here weighted by the probability of occurrence. So we have both the probability outside the function and also inside the log function as an argument, and that forms us the entropy. It characterizes a random variable and what is the average amount of information of the random variable weighted. Its information content weighted by its probability distribution. Let's have a look at what this means actually. So we have here an example of a uniform distribution of a discrete random variable where we have 8 different states and each state is occurring at the same probability. So and the probability is therefore 1/8. So let's have a look at what the entropy is calculating. The entropy is calculating the, again, average amount of information in these binary digit bits. And we can see here that it is the sum of 8 times, because for each value of this random variable is the probability distribution times the log 2 probability for that given value, and then minus logarithm here. And that actually leads to the value of 3, because here we have the log 2 of 1/8 is 3, and so log 2 of 8 is 3. So here we have powered by -1, which we put inside. So there will be 8 here, and so we have 3 bits. That means that is the 3 bits is the average number of information, and that means also that for 8 different values, we would, in binary digits, we would need 3 bits to encode it, which is also true because in binary code, we will have values of 1, 2, 3, 4, 5, 6, 7, 8 encoded by 3 digits. Let's have a look at another example where we can see that we have still 8 states which the discrete random variable is achieving. However, here we do not have a random variable, but we instead uniform distribution. Here we have a distribution which is non-uniform. So obviously the A is occurring the most often times, second is B, then C, then D, and then E, F, G, H occur at a very low probability with both with the same value. So there will be associated with high information content. So let's calculate what will be the entropy of this random variable given its probability distribution. And we can see that we are here having always the product of the probability log probability for each of these values of the random variable. And that leads to a value of 2 bits. So, and that is an interesting outcome, where we can see that the entropy has, although we have still a random variable of 8 states, has changed because the probability distribution has changed, and the probability distribution is no longer uniform. So it means that we need on average 2 bits in order to transmit information of this discrete variable. On average, not overall. So let's have a look at this in detail, what it means. So imagine that we can code this discrete random variable with the binary code. And this binary code will be designed in such a way that we use for A just 1 digit, the 0, and then for B we are using 2 digits, 1 and 0. The 2 digits, obviously if we would use 1 digit, then we have already used up the coding, because the digit coding has to be distinguishable. So if 0 is used for A, then we have to have for the others have to start with not non-zero value, with 1, and then for that we will use 0 for the B, and then for C we will use 1, and we cannot use 0, we cannot use 1 0, so we use 1 1 and 0 for the C, and for D analogously we use 1 1 1 0. For D we use 1 1 1 1 1 0 0. So here we are using already 6 values, and then we are using 6 values here, and we are using 6 values here and here. So this is a efficient coding of this random variable given its probability distribution. And now if we look at it, so the 1/2 is using just 1 digit, 1/4 is using 2 digits, then 1/8 probability, so that C is using 3 digits, and so on, which actually equals to the average value of 2. So we are using on average only 2 bits to transmit information, because in 50% of cases we are using just 1 digit, and then the rest is then average that we are using on average 2 digits. Now let's turn the discussion from the logarithm of a basis 2 to a natural logarithm, as we are used to from the previous conversations. So we will still be talking about entropy, but we will be measuring entropy not in bits, but let's call it in knots. And here we have therefore an analogous formulation of this entropy, which will lead to slightly different values, as the logarithm has a different base, but it is behaving in the same way. It's proportional to the to entropy with any other logarithm base. Let's have a look here at when do we achieve maximal entropy. If we look at in these cases here, we see that the maximum entropy is somehow seems to be achieved when our distribution is sort of equally distributed among all the values of these random variables. So here we have a highly non-uniform distribution where we have a very high likelihood of a certain values of a random variable, while for others we have 0. And when we have much more balanced distribution, coming to the uniform distribution closely, then we have a high entropy value. So let's perform the search for the maximum in the same way as we did it before for searching for maximal values of a certain weights or minimal values in terms of minimal errors. So what we will do here, we will be performing a derivative of the entropy with respect to px, and then we will be setting it to 0. However, we will at this point need to introduce this Lagrange multiplier approach, where if we have by introducing constraints into the equation. And in fact, we have already done this in the case of regularization, where we have also introduced the constraint that our W should be minimal back in the lecture over a week ago. Now, here we have a constraint that the sum of the probabilities is equal to 1, and that is introduced into this equation. We want to optimize by the constraint weighted by a parameter lambda. So let's have a look at what happens if we derive this term and if we set it to 0. So this is then a partial derivative of a certain pxi. So for a given value of x of this function which we have defined with this constraint with lambda. Well, in this sum which we had in this term, all terms will be equal to 0 unless the term which is particularly concerned with the pxi, so where there is one particular value of x reached. So that term will be non-zero, and that term will then lead, just this is the minus pxi times ln pxi will lead to so this is a multiplication which we are deriving, and first we are deriving the first part and the second part not. So the pxi is derived to 1, and we will then have the first term ln pxi, and then we keep the first term pxi not derived, and the second term ln pxi is derived into 1 divided by pxi, which we have numerator pxi, denominator pxi, so that is equal to 1. So here we have the derivative of that part, and the lambda associated with this 1 pxi will be then taken as the multiplier of this pxi, and that is the partial derivative with respect to this particular value reached by the random variable, and that is equal to 0. Now, if that is equal to 0, then the ln pxi is equal to lambda minus 1, and that implies that pxi is equal to e powered by lambda minus 1. And we also know that the constraint defined that this sum of all the probabilities of random variable values is 1. So that means that the sum of this term is 1, and that means that n times this value is equal to 1. So this one is therefore equal to 1 divided by n, and this term, e powered lambda minus 1, we can again say it's equal to pxi, which is then equal to 1 divided by n. So this means that for discrete random variable, the highest entropy value is associated with the uniform distribution, where the probability for this particular value of the random variable, but also for any other value of the random variable, will be always 1 divided by n. So that is a characterization of this quantity called entropy, which is telling us what is the average number of information which in terms of bits, for example, uh, which we need for transmitting certain random variable. Now we can look at this quantity also for the continuous random variable case, and here we are not um, um, dealing with a discrete set of states, but we are having a continuum of states, which also means that somehow if we have like an infinitely long real number value, we will need also infinitely long bits for that. So this entropy value might be very high in some context. So let's have a look at this situation where we first say that while we have a certain integral of px, we can say that this integral is equal to some like we have a certain bin on the real axis, which is described by this value delta, and we are using the mean value theorem, which will be characterizing us that this delta is is a certain bin width, and then the probability is a certain height, and there is for sure a certain probability in the probability density function, which will correspond to the integral of this area over this function. So this area is equal, which has maybe a more complex shape, is equal to just a let's say area of a rectangle of this bin for a certain height of probability within this interval of this I to I plus 1 of this bin value. So we can see that the probability continuous variable x is assigned to xi bin when it belongs to this ith bin with the probability of the bin of the probability of pxi and delta. So in this way, we have turned this continuous case again into a sum instead of integral, because we replace this integration with the sum of these areas of rectangles, which is then defined by this delta and pxi for certain xi within this bin. And then the entropy for this case is then equal to pxi delta ln pxi delta, and we can see that we can in fact take out the ln out of ln this value ln delta, and we end up in something which is very similar to our discrete version of entropy. Here, this term we could have taken out of the sum in such a way that we are taking this multiplication here, but we have the negative sign here, so that's a negative ln delta, but it would be still in the associated with the sum by this term pxi delta, and but the pxi delta will in sum be equal to 1, because that's the probability distribution of this continuous random variable will be then for all the bins equal to 1. So that's fine. And then imagine that we are this delta is of a certain width, and now if we want to perform the discrete case turn back into the infinitely small delta, we will end up again in the integral formulation. So the delta is by limit going to 0, and we end up in the term where this is now an integral px ln px, and that is called the so-called differential entropy. And this differential entropy is then not the same as the regular entropy because of this term ln delta, where if we are making smaller and smaller delta, we are in fact using a larger and larger precision of our real values, and in case of infinite precision, this ln 0 will end up in a very high value, will lead to infinity. So this term will make this entropy become very high. But for the other part of this calculation of entropy, this differential entropy is characterized in the same way as the regular entropy. So we see that the continuous case is then different from the discrete case by this term ln delta. Now, finally, let's go ahead and find out what will be the maximal value of the differential entropy when what would be the probability distribution. Again, let's set up certain constraints into our search for maximal value. So first of all, the probability distribution needs to be equal to 1. Then the probability distribution has a fixed value of mean, and the probability distribution has some fixed value of the variance. And now, if we are going to look at this this maximization, and we again derive it with respect to certain px, we see that we have a similar situation where we are having this integral of px ln px, and then we have the one constraint associated with lambda 1, then we have another constraint associated with lambda 2, and this is the fixed mean constraint, this is the fixed variance constraint, which is associated with lambda 3. And we derive this and set everything to 0. The derivative is leading to a very similar situation as we had before when we performed the derivative of entropy. And here we can see that the ln px is equal to 1 minus lambda 1, lambda 2x, lambda 3x minus mu squared. So previously we just had these two terms, which we then put on the right hand side, but now observe that we have another constraint, and then this another constraint is then leading to just leaving us with the lambda x, and then because it is then weighted by the px, and also here lambda 3 is lambda 3 x minus mu squared, because also it was weighted by the px. By the derivation it was removed, so we are ending up with this long term. Out of this we can see that the px is equal to this formula, and with this sum in the exponent, and we can observe what is happening to this exponent. So we will not go into detail of that, but to satisfy the finite mean and variance, it turns out that the lambda 2 has to equal to 0, so we will then lose this term, and then we have only this term, and we have this term. So we can recognize here that we are dealing with some exponential function, and we have here this x minus mu squared, which is leading our thoughts to the normal distribution. So imagine that we have like this term here will be e powered by minus 1 plus lambda 1 will be a, certain a. Then we have this term, but this term will be just 1, because the lambda 2 will be 0, and this term we will be then searching for, and the whole thing should be equal to to this probability distribution. Now, if we are putting back this values of the px into the integral, which we started up first with, then for a integral of from minus infinity to infinity of this exponential function, the result is square root of pi divided by minus lambda 3. And in order that this, we have the first constraint, which tells us that the overall probability distribution has to be equal to 1, then the result is that the a must be equal to this value. And so we need to express what is the value of the lambda 3. If we have a look at the other term, other constraint associated with the variance, we see that the variance associated with this probability distribution P of px, we already know that, and then from that it comes out that this is equal to 1/2 of minus lambda 3, which has to be equal to this fixed variance. And out of that, we will it will become clear that lambda 3 is minus 1/2 sigma squared. And we end up with our normal distribution here. So for the differential entropy, the highest value is associated with the normal distribution. And now in more detail, we know that the highest value of differential entropy will be associated with the normal distribution. But what is the highest? How does it somehow scale? So let's have a look at this once again. We have this probability distribution, and now we are what will be the associated entropy of this. So here we can see that we can if we are performing the logarithm here, then the exponent will come out as the separate term here out of the logarithm, and then we will have this logarithm here, negative logarithm here expressed, because this is in the denominator. That's why the negative logarithm here. So we have this term, and then we have this term here, which first part we can take this term out of the equation, and then we have just integral px dx, and then we have the other integral here, which is px x minus mu squared dx. And we know that this integral is equal to what? This is equal to 1. So we have this one term, and then for this other term, we see that what is this? This is equal to variance, and that is equal to sigma squared. So we have here this term will be then multiplied. This term will be then multiplied by the sigma squared, and so we will have here just 1/2. So we can take then 1/2 in the front, and we will have the value of what will be reached by the entropy given this distribution. And we can see that it scales with the sigma. So for large sigma, we will have a larger and larger entropy, differential entropy value. And this entropy is no longer always positive, as it was the case for the discrete random variable. It can be also negative, and that is in case the value of this term is bigger. I mean, it's smaller than -1. In information theory, we can also look at the joint distributions of multiple random variables to quantify their information content or average information of this joint distribution. And similarly, we can also express quantities like conditional entropy, for example, which is measuring the additional average information needed to specify y, provided that we already know the outcome of x. So once again, here is the conditional entropy, and we have a joint distribution of the two random variables, but we already have received information about x. And the question is, what is the average additional information needed to specify y, as these are these two random variables are not generally independent, and this is expressed by this quantity conditional entropy. So as we are dealing with average, we can use the concept of expectation over the joint probability distribution, and we have as a function the negative logarithm of this conditional probability. So this will lead into a double integral of kind of a mixed terms between the probability and the probability in the argument of the logarithm. But because we need to perform the integration over the joint probability distribution. However, we can reformulate this conditional entropy also in the term of two nested integrals, where we have this conditional probability distribution here also for the weighting factor of the information value, but this is also then multiplied, the result of this integral is multiplied by the px, which is taken out, which is marginalized out of the integral. So let's have a look how this conditional entropy holds with respect to the previously mentioned definition. So we have here joint entropy. Here we have the conditional entropy, which is the average additional information needed to specify y after we already know x. And these two terms are expressed here through their integral formulation. So we can see here is the joint entropy specified, and here is the conditional entropy specified. Now, as one is subtracting from the other, we can also, and they have a very same form, so we have the probability distribution, which is the joint in both cases, and we have the logarithm. We can put it also under one double integral, where we have the conditional probability in the denominator, and with this formulation here, we obtain an probability distribution of ln px. So this will result into px, because joint probability distribution is equal to, so pxy is equal to px times py given x. So this fraction will give us px, and it is ln px, and we have it here outside the integral with respect to dy. And we are left with then with this joint probability distribution. The ln term is out of this inner integral. And this inner integral actually is leads into a marginal probability distribution with respect to x, because we are integrating over all y. So we end up with a single integral of px ln px dx, which is actually the differential entropy of with respect to the single variable x. So we can see that hx plus hy given already known x will lead to hxy, which is the joint entropy. So this expression holds. And the joint entropy can be defined as the information needed to describe x and y is as a sum of information about x, which is the hx, plus remaining information about y given x, which is the conditional entropy. Let's now relate the concepts from information theory to pattern recognition. Imagine that we have a true distribution of some random variable which is p, but we don't know this true distribution. But we are approximating this true distribution by approximating distribution q. And we can use now the concepts from information theory to express the relationship between these two probability distributions, the true distribution P and the approximation distribution Q. And this can be done through the so-called Kullback-Leibler divergence, which is also called as a relative entropy that measures the similarity between these two distributions. It can be formally defined as the Kullback-Leibler divergence between P and Q as the subtraction of one entropy with respect to another entropy, where in this one entropy term we have the probability distribution px of the information associated with the probability distribution described by qx. So, and we can see like what is, if we already know the QX, how much information is still out there which is not described, which is not describing fully the true distribution PX. So we can reformulate this sum of two integral terms into one single integral where the PX probability distribution will be in the denominator and the QX, the approximating distribution, will be in the numerator of the logarithm. And this measure, Kullback-Leibler divergence, is we can see here how this expresses the kind of the residual information. And imagine that these two values, these two probability distributions are equal, then obviously these two terms will be equal to each other, and then the result will be 0. So the Kullback-Leibler divergence is equal to 0 if the Q and P distributions are identical. And it is non-zero and bigger than, and it's positive, if these two are not identical. Please note that this is not a true measure, as the Kullback-Leibler divergence is not a symmetric measure. So we will have a different result if we will switch the P and Q, as obviously this comes from the this comes out from this term, where he will have a reciprocal of these two terms, and here in fact we will have the QX instead. So we have stated that this KL divergence is a positive measure, so it always ends up either in 0 in case the two distributions are equal, or in some non-zero positive value. So, but why is this the case? For that, let's review shortly the definition of the so-called convex function. Convex function is a function where the function itself lies on or below the so-called chord line. The chord line is a connection of two functional values on anywhere on this function, and it's an interpolated line between these two functional values. So you can imagine it like a linear interpolation with a parameter lambda, which is varying between 0 and 1, where we are waiting first the first functional value associated with the value of x equal a, and plus the 1 minus lambda associated with the function when the x has the value of b. And this is always bigger, so it's above the functional value evaluated somewhere in the interval between a and b. So imagine that this lambda has a certain value, maybe here something like 0.55, and we can see that the x lambda here is calculated as 0.45, then 0.45 times a plus 0.55 times b. This will be its value, and then the function of that will be here. While with the same lambda parameters, if we are interpolating the functional values, we will end up above here. And it can be shown that this holds not only for 2 points, but for arbitrary points on the function, that the result of this inequality holds. The chord line is always above the function itself, or in the worst case on it. And this holds for lambdas which are bigger than 0 as interpolated function, and in sum they are equal to 1. So this information about the convex functions can now be used for or this formulation, to be more precise, can be now used for expressing the Kullback-Leiber divergence. Let's have a look at this. This inequality, which we have been talking about, is the so-called Jensen's inequality, which is relating this convex function definition, the position of the chord line with respect to the function. And it also imagine that if we have as the functional value, so the lambdas here, which were previously just parameters, if we will have it, if we use the probability distributions over x, then we will in fact have here that the x times px, so instead of lambda I, we will have the px associated with this random variable, the probability of this occurrence of that particular value. Then we will have an expectation here, and we can see that function of an expectation of an average is smaller than expectation of the functions themselves, of the function of this random variable. So here we will have the function f being some function for now, but its expectation of this function will be larger than expectation of x and the function of that. So that's the direct outcome of this Jensen's inequality when we consider the lambdas as the probability distribution over x. And here we can see it in more detail, where we have the definition of expectation and the function of that, and we have the expectation of this function and the definition of an expectation of fx. Now, if we apply this Jensen's inequality to KL divergence, and the function fx is actually the minus negative ln x, then we can consider the following formula. So we have a function of minus ln x, and then in integral we have the fx, the argument of the function is qx divided by px times the px dx. So here we see that we are just having the denominator and the one more px here, which can be cancelled out. And we will be left out integral of qx dx, which is actually equal to 1, and this will then be equal to 0, is smaller than, and we have here the integral of px qx divided by ln x. So here is the fx inside the integral and as the expectation, and it's forming in fact this KL divergence. So this will tell us that this term is 0 and this is bigger than 0. We have it also reformulated here so that it becomes clear. So this term is simplified, this term, and from that it implies that the KL divergence is a positive measure. It is important to say that for proving this fact that KL divergence is a positive measure, we have used this convex function definition and this Jensen's inequality, and in that we had the function, that function had to be convex, this fx, and for fx we had this function negative ln, which is a strictly convex function. So with that, we were able to prove the fact that the KL divergence, the strictly positive measure, that was only under the condition that the negative ln x is a strictly positive, strictly convex function. So suppose that we have data generated by this unknown probability distribution P, and which leads into some points or data values of xn, and so it's a representative of this probability distribution Px, which is unknown. And if we want to use the KL divergence, we can measure, based on these points, how far is this approximating distribution from the true distribution Px, and say that this approximating distribution Qx is having some parameters theta for defining this distribution. Like, for example, in a normal distribution, that would be the mean and the standard deviation. So in such a case, we can reformulate the KL divergence into the sum of these individual data points probability distributions and the logarithm of it, and our known approximating distribution Q with the corresponding value x. Now, for finding the best match of the function Q, finding the optimal parameters, let's say that the function Q is a normal distribution with some parameters, so finding the optimal parameters for mean and variance or standard deviation, we can simply minimize the KL divergence, and we will find out by, so we can, as this is negative log, so it actually relates to like a negative log likelihood estimation, because if we will perform derivative of this expression with respect to, let's say, mu, or with respect to some theta parameter, then we will see that only this term will be represented and this term will disappear from the sum. And that means that, as we observe here, this is negative log a function of our probability distribution, for which we are finding the most appropriate parameters. So minimizing KL divergence is equivalent to maximum likelihood estimation, where we are also performing the logarithm of a function and then setting it to 0. And of course, it is negative log likelihood, so it will be like a minimal value of KL. And with minimizing KL, it means that we will be coming closer and closer from this of the approximating distribution Q to the true distribution P. Furthermore, we can utilize the KL divergence measure for evaluating how independent two probability distributions of two random variables are. So if they are independent, then the joint distribution Pxy is equal to the product of Px with Py, and we can use the KL divergence to see how this equality holds, in the sense that we have here one joint distribution, and here the other distribution. Previously here was just a Qx and here was a Px, so the Qx now, the approximating distribution is the joint distribution, and here it's a product of two probability distributions of these two random variables, and we are evaluating how this what is the value of this term. So as it is a KL divergence, it will be 0 or a positive value, and it will be 0 only if this term will be equal to 1. So in that case, the ln value will be 0, and this whole integral will be 0. So then indeed the product of px and py will have to be equal to the joint distribution of x and y. However, if these are different somehow, then this term will be not equal to 1, and then we will have not equal value of 0, and therefore this whole double integral will be then some positive value. And this positive value is the so-called mutual information, and it is the degree of correlation of the two distributions of random variables x and y. Degree of correlation means that if they are equal to 0, there is no correlation between these two random variables, and they could be correlated only partially, and mutual information quantifies this degree of correlation. Also, there is a relationship between the entropy and the mutual information in the following way, where we can see that the entropy is equal to the mutual information is equal to entropy of x subtracted by the conditional entropy of x after we know the observation y. So, and here it is described how this comes to place. So here this function is the mutual information but described in 3 integrals. So this is one integral. This is then in the logarithm there will be times px times py. So this is this part, and then these are the products of px py, but just separated into 2 integrals. And here is the denominator, the pxy, the joint distribution. And we can see here negative, negative, positive. So because this is in the denominator, the pxy. And if we look at this, then we can take out if this is the inner is the integral over y, we can take the ln px out of this integral, and then the joint distribution integrated over y will simply be marginal distribution with respect to x. So then we have in this integral px ln x ln px, and this is simply the entropy of x, and then we have here, this is actually the entropy of y. We are just having the inner integral will be the over x instead of over y. So here is the entropy with respect to y, and this term is actually the so-called joint entropy, which is expressed here. So our mutual information can be expressed as the sum of the two random entropies of the random variables subtracted by the joint entropy, and this can be also reformulated because this is actually the formula for the conditional entropy as entropy of x minus the conditional entropy of x given we know the observation y. And this is the mutual information which represents the reduction in uncertainty about x after new observation y. So the reduction of uncertainty about x. And of course this is symmetric if we express it in terms of hx minus hxy. Here we will this will result into the conditional entropy Hy after observation X, and then we will have a very similar formulation of subtraction of Hy minus Hy given X, similarly as it is described here for X. And that will then represent the reduction in uncertainty about Y after new observation X. And of course, we can always relate these random variables and the probability distributions to the probability theory. And in the Bayesian perspective, we have the px related to the prior distribution, and the px given y is the posterior distribution after observing the new data y. And therefore, this is how the information theory comes into place in order to understanding how this uncertainty is changing after new observations of y unknown, and what does it have to do with x, provided these two random distributions are not independent. And this is the end of the chapter 1 of the book Pattern Recognition and Machine Learning by Christopher Bishop. And we will be continuing with the second chapter on probability distributions.